Welcome back to The Sleepy Scientist, a quiet corner of the universe where you can rest, unwind, and drift towards sleep while learning something calming and wonderful. As you settle in and get comfortable, this evening's journey takes you far beyond the warm inner planets, out past the giant worlds, and deep into the soft outer dark where a tiny world waits with a surprising amount of beauty and mystery. Tonight, you and Pluto will keep each other company. Before we drift any further, may I ask where in the world you're watching from tonight? I always love seeing how far these peaceful science journeys travel, and if you enjoy these quiet explorations, a gentle like and a subscribe really helps this little channel continue growing across the cosmos. To everyone who has already joined this sleepy community, thank you so much. Please do tap the notification bell as well so you do not miss the next calm adventure. I will do my best to keep this soothing and restful, but every now and then the universe becomes so fascinating that it might hold your attention a little more than planned. If this one keeps you awake for a moment or two, at least you will drift off slightly wiser than when you arrived. As you and Pluto begin this quiet journey together, here is something to wonder about as you settle deeper into the dark. How did such a tiny, distant world end up reshaping the story of our entire solar system? Pluto sits so far away that sunlight takes hours to reach it, and yet this small, frozen world has captured more curiosity and emotion than worlds many times its size. In the soft silence of the outer dark, it moves along its stretched-out path with a calm patience that almost feels timeless. This introduction eases you gently into that distant environment, preparing the mind to slow down and settle into the long rhythm of a place where seasons last decades and shadows stretch for miles. Here you begin to understand why Pluto became such a point of fascination. A world discovered by studying faint specks on old photographic plates. A world whose size was misunderstood for decades. A world that turned out to be far more alive, far more complex, and far more surprising than anyone expected. And a world that, despite being demoted from the list of planets, still holds an emotional place in the hearts of people all over the world. This quiet moment is where the journey takes shape, not through facts alone, but through gentle curiosity, through the feeling of drifting outward, letting the noise of daily life fade behind you, and allowing your thoughts to move slowly enough to notice the details of a frozen world that sits on the threshold between what is known and what is still waiting to be discovered. As you settle further in, one question begins to guide the journey forward. What makes Pluto, of all the distant worlds, so astonishing once you finally see it up close? The journey outward begins gently, almost without you noticing, the way twilight slips into night. You start in the familiar warmth of the inner solar system, a place of bright sunlight and quick orbits, where planets circle the sun in tidy, predictable paths. But as you drift farther from that comfortable centre, the light softens. The space between worlds grows wider. The sun becomes a little smaller, a little dimmer, a little less commanding with every million miles you travel. There is no sudden change, only a long, steady quieting, as though someone is slowly turning down the brightness of the universe. The warmth that once wrapped the inner planets fades first. In those close regions, sunlight pours onto the rocky surfaces of Mercury, Venus, Earth, and Mars at strengths and temperatures that can shape landscapes, stir atmospheres, and carve entire climates. But as you drift outward, the grip of sunlight loosens. It falls away in gentle steps, thinning into something pale and cool, By the time you reach the orbit of Jupiter, the sun feels more like a distant lamp than a nearby star, and even this fading light will seem bright compared with what lies ahead. Still you drift outward, past the gas giants with their broad, swirling atmospheres and deep, complex storms. These worlds remain familiar in their own way, massive, colourful, full of motion and activity. They each carry families of moons, miniature systems moving in harmony around them. They feel alive, dynamic, almost crowded, even out in this colder realm. But beyond them the scene changes. Once you pass the orbit of Neptune, the last of the giant worlds, the solar system begins to stretch and open. Everything becomes quieter. Space itself seems to widen into something gentler and more hushed. Here, sunlight becomes the faintest whisper. It still travels outward, still reaches every corner of the solar system, but by the time it arrives this far out it is weak enough that an afternoon on Pluto receives about the same warmth as Earth would feel from a sunset more than 3,000 times dimmer. The glow that once supported oceans, forests, storms and seasons becomes a pale silver thread, barely enough to light the ground. If you held out your hand here, you would still see it, but only faintly, as though lit by a winter sky just before night takes over completely. The temperature follows the light. Close to the sun, heat shapes everything. It melts ice, drives winds, freezes and thaws water, and sculpts the surfaces of planets over time. But out here, heat has very little to work with. The cold deepens steadily as the distance grows, until it sinks to levels where gases like nitrogen and methane, which are airy and playful on Earth, settle onto the ground as solid ice. Even shadows behave differently. They do not just darken the landscape, they harden it. A place that spends too long without sunshine becomes colder still, locking the surface into patterns of frost and frozen air. As you move farther from Neptune, the feeling of space changes entirely. The planets near the Sun are relatively close neighbours, separated by distances that seem large only until you compare them with what lies in the outer dark. Out here, the gaps grow so immense they become almost abstract. Between Neptune and Pluto is a gulf so wide that a journey across it would take years at the speed of a modern spacecraft. And Pluto is not even at the true edge. Beyond Pluto stretches a vast region filled with icy debris, ancient leftovers from the early solar system, scattered across distances so great that no single glance could take it all in. This is the beginning of the Kuiper Belt, a ring of frozen bodies circling the Sun in a broad, quiet arc. Some are as small as mountains, others are large enough to be worlds of their own. But none of them glow, none shine brightly, and none give off heat. They drift silently through cold, thin sunlight, each one minding its own slow orbit. It is a place where time feels stretched, where nothing seems urgent, and where worlds can take millions of years to change their surfaces even slightly. As you glide through this region, you notice something about the silence. It is not empty, it is peaceful. The planets of the inner solar system feel busy, full of storms, collisions, eruptions, and weather. But the outer regions hold themselves with a different kind of presence. They feel steady, serene, and ancient, as though they are keeping secrets from the earliest days of the solar system. Here, distance becomes a kind of cushion. Light travels for hours to reach these worlds, and everything that happens does so at a slower rhythm. Even the orbits stretch into vast, gentle loops that take centuries to complete. This slow shift from the familiar to the unknown is where the journey truly takes shape. you begin to realize how small the warm inner worlds are compared with the enormous space that surrounds them. The majority of the solar system is not bright or warm or crowded. It is this, a wide, quiet expanse where sunlight arrives in thin, silvery beams, and the cold settles softly into everything it touches. The planets you know feel like islands compared with this great dark ocean, and yet it is in this stillness that Pluto lives, a tiny world drifting through a space so large it almost seems endless, illuminated by a sun that is no longer a fire but a distant star. If you were standing on its surface, the sun would look like a bright dot you could cover with the tip of your finger. But even at this distance, even at this cold, Pluto is not a frozen relic or a dead rock. It is part of a complex, graceful region filled with ancient objects and untold stories. All of this builds toward the gentle realization that Pluto is not an outcast at all. It is a citizen of the outer solar system, living in a landscape shaped less by heat and more by time. Its neighborhood is vast and quiet, but it is not empty. It is a region of frozen plains, drifting worlds, and the faintest touch of sunlight, stretched across unimaginable distances. A place that asks you to slow down, breathe softly, and take in the scale of everything around you. And as the cold grows deeper and the light grows dimmer, one question begins to form in the silence. What kind of world could take shape in a place this far from the warmth of the sun? The idea that something waited beyond Neptune began long before Pluto ever appeared on a photographic plate. It started with a feeling, a suspicion carried quietly through observatories in the late 1800s and early 1900s. Astronomers studying the orbits of Uranus and Neptune noticed small irregularities, tiny deviations that did not quite match the predictions made by Newton's laws. These were not dramatic shifts, nothing that would catch the eye of a casual observer, but to a patient astronomer they stood out like faint ripples on a still pond. Something, they believed, was tugging at the outer planets, something faint, distant, and heavy enough to leave fingerprints in their orbits. At the time, this was not an unusual line of reasoning. After all, Neptune itself had been discovered because of the way its gravity pulled on Uranus. Astronomers had looked at the irregular motions of Uranus, performed careful calculations, and correctly predicted that another planet must be hiding in the darkness. When they pointed their telescopes toward the exact region the equation suggested, Neptune appeared. It was a triumph of mathematics and patience, and the memory of that discovery lingered in the minds of astronomers for decades. If it worked once, perhaps it could work again. One of the people most captivated by this idea was Percival Lowell, a man with an intense curiosity about the solar system and a great willingness to chase mysteries that others found too faint or too strange. Lowell had already become famous for his controversial ideas about canals on Mars, but his attention gradually shifted toward the far edges of the solar system. He was convinced that another world existed beyond Neptune, a world whose gravitational pull was responsible for the small but persistent quirks in the orbits of the giant planets. Lowell gave this hypothetical world a name that would echo for decades: Planet X. The letter was not chosen for dramatic effect, though it certainly gave the idea a sense of intrigue. In astronomy, the letter X simply stood for unknown, but the imagery stuck. Planet X sounded mysterious, important, something almost myth-like. It could have been large or small, bright or dim, but the truth was that no one knew. Lowell saw it not as a fantasy, but as a problem waiting to be solved. He approached the idea with careful calculation. Using the observed motions of Uranus and Neptune, he attempted to determine where this unknown planet might be hiding. His math led him to a rough patch of sky, a region where he believed a new world might pass. But finding it would not be easy. Even with the best telescopes available at the time, faint distant objects looked like tiny dots of light barely different from stars. To find a moving world among them, you had to compare photographs taken days or weeks apart and search for a single dot that had shifted slightly. It was slow, delicate work, the kind that required a steady mind and extraordinary patience. Lowell began a long campaign of sky surveys, capturing photographic plates of the night sky and searching them for any sign of movement. Plate after plate was developed, examined, catalogued, and filed. He wrote extensively about his predictions, refining them as new data came in. His observatory in Flagstaff, perched high in the thin air of Arizona, became the quiet center of the search. Yet despite his dedication, Planet X refused to reveal itself. Night after night, Lowell's team scanned through the glittering fields of stars, looking for a faint drifting point of light. The search stretched over years, yielding nothing conclusive. The sky simply held too many dots, and each photographic plate captured thousands of stars, any of which could easily be mistaken for a planet if the comparison between plates was even slightly off. It was like trying to find a tiny speck of dust on a tiled floor, where every tile looked almost identical, and the speck might not even be there at all. Still, Lowell remained confident. He believed that his calculations were correct, that the oddities in Neptune's orbit meant something real was out there. His notes grew increasingly detailed, his predictions more refined. But even as he narrowed his search, his health declined. He continued working, convinced he was on the edge of a discovery that would reshape the solar system. When he passed away in 1916, Planet X remained hidden, and the search fell silent for a time. Even so, Lowell's work did not disappear. His calculations, his predictions, his sky photographs, all of them remained preserved at the observatory. Other astronomers, curious about the mystery he left behind, continued to discuss the possibility of a ninth planet. Some doubted it. Others found the idea too tempting to dismiss. The notion of a hidden world tugged at the imagination, and the slight irregularities in planetary orbits kept the discussion alive. Over the next decade, the search resumed in quiet intervals. Astronomers re-examined plates, rechecked Lowell's math, and gathered new observations. Yet, for all the effort, Planet X still refused to show itself. Some began to suspect that the irregularities Lowell had relied on were not caused by a hidden planet at all, but by slight errors in measurements or limitations in the data. The outer solar system was simply too far away, too dim, and too poorly understood for anyone to be completely certain. Then came a new generation of sky surveys, using sharper equipment and more careful procedures. Among those involved was a young assistant at Lowell Observatory named Clyde Tombaugh. He was given the task of systematically photographing sections of the sky and comparing the images for any sign of movement. It was exactly the kind of patient, meticulous work that Lowell had pioneered, but now performed with slightly improved tools and a set of more refined expectations. Each pair of plates revealed countless stars frozen in place, but Tombaugh continued with absolute discipline. He scanned every square millimeter with an unwavering focus, looking for the faintest shift. And months into his search, he noticed something small, just a tiny speck of light, moving against the backdrop of fixed stars. It was subtle, almost easy to overlook, but there it was, a slow, steady drift. What Tombor found was Pluto. The world Lowell had spent years hoping to discover had finally revealed itself to another set of eyes. It was smaller and fainter than Lowell expected, far less massive than his calculations had predicted, but it was real. After decades of searching, the idea of Planet X had finally led to an actual world. But it is important to realize that Pluto was not discovered by accident. It was found because of years of groundwork laid by astronomers who believed the outer solar system held secrets worth uncovering. Even though Lowell's calculations were not perfect, his determination and dedication pointed others toward the possibility of something waiting beyond Neptune. And so the long road to Pluto began with a question, a suspicion, and a man who refused to let faint irregularities go unexplained. That quiet persistence eventually brought a tiny distant world into view, one that would go on to challenge expectations, reshape definitions, and spark some of the most passionate debates in modern astronomy. But before any of that could happen, one puzzle had to be answered. What exactly had astronomers found out there in the cold dark, drifting so quietly at the edge of everything? Clyde Tombaug's path to discovering Pluto did not begin with an advanced university education or a powerful research grant. It began on a farm in Kansas, where the night sky stretched wide and clear above the fields. As a teenager, he built his own telescopes by hand, grinding and polishing the mirrors himself with the kind of patience that would later define his scientific career. He studied the sky with quiet dedication, sketching detailed drawings of Jupiter and Mars, not because anyone required it, but because he felt compelled to capture what he saw with the greatest accuracy he could manage. Those sketches, made with steady hands and a careful eye, eventually found their way to Lowell Observatory in Arizona. The observatory staff, impressed by the precision and commitment behind the drawings, invited him to join as an assistant. It was a remarkable moment, a young man with no formal degree, stepping into the world of professional astronomy through sheer perseverance. When Tombaugh arrived at Lowell Observatory in 1929, he was given a task that was as monumental as it was repetitive. He was to continue the search for the mysterious Planet X, the world Percival Lowell believed was lurking beyond Neptune. The observatory had the equipment, the sky charts, and years of calculations pointing to possible locations of the hidden world. What they needed was someone with both the endurance and the sharp attention to detail required for the final, most difficult step. They needed someone who could look at thousands of tiny points of light and spot the one that did not belong. The tool Tombaugh relied on was called a blink comparator, a device that allowed him to compare two photographic plates of the same patch of sky taken at different times. When the images were placed side by side in the comparator, a mechanism let him blink rapidly between them. Stars remained fixed in place, perfectly aligned in both images, but any object that had moved during the interval between exposures would appear to jump slightly from one image to the other. It was a simple concept, but the execution required immense patience. Each photographic plate captured tens of thousands of stars. Each pair of plates had to be examined slowly, square by square, with complete focus. This was the work Tombaugh did day after day and hour after hour. He would lean over the blink comparator, adjusting the focus, blinking through sections of the sky again and again, scanning for the faintest hint of movement. The task could have easily overwhelmed someone with less determination. The plates were large, the fields crowded, and the possibility of finding a distant icy world was not guaranteed. But Tombaugh was steady. He worked with quiet persistence, moving methodically through every image, trusting that careful observation would eventually reveal something hidden. Then, on a cold evening in February of 1930, as he blinked through yet another pair of plates taken weeks apart, he noticed a tiny speck of light shift slightly. It was not dramatic. It was not even easy to see at first, but it moved. A star stays still. A planet drifts. Tombor marked the dot, checked it again, and confirmed the motion. What he saw was not a star, not an artifact, not a smudge or flaw in the plate. It was an object moving steadily against the background of fixed stars. He had found something. Tombor did not rush to announce his discovery. Instead, he prepared a series of careful checks, confirming that the moving speck behaved consistently over multiple observations. He traced its motion across the plates, watched it inch along its distant orbit, and documented everything meticulously. Only when he was absolutely certain did he bring the results to the observatory's director. The reaction inside Lowell Observatory was a mix of excitement and disbelief. After decades of searching, calculations and speculation, a new world had finally appeared. The observatory kept the discovery secret for several weeks, while additional observations were made to confirm its orbit. This was not simply a small asteroid or a passing fragment of rock. It was something more substantial. It was far away, well beyond Neptune, and moving with the slow grace expected of a distant planetary body. When the news was finally announced to the public on March 13, 1930, it made headlines around the world. Newspapers ran stories celebrating the first new planet discovered in the solar system since Neptune in 1846. People were thrilled by the idea of a hidden world brought into view by a young astronomer with homemade telescopes in his past and a blink comparator at his side. The question of what to name this new world drew enormous interest. Suggestions poured in from across the globe. In England, an 11-year-old girl named Venetia Burney proposed the name Pluto. She chose it not only because the god of the underworld lived in a distant shadowed realm, but also because the first two letters matched the initials of Percival Lowell, whose efforts had laid the foundation for the search. The name caught the attention of astronomers at Lowell Observatory, and within weeks it was officially adopted. Pluto fit perfectly, mythological, evocative, and subtly tied to the man who had dreamed it into the scientific conversation decades earlier. As soon as Pluto was named, it was welcomed into the family of planets without hesitation. In the 1930s, the solar system was understood very differently. Pluto was believed to be roughly the size of Earth's moon, or perhaps larger. Many astronomers assumed it might even rival Mars in mass. Only later, as measurement techniques improved, did the scientific community realize just how small Pluto truly was. But in those early days, size mattered less than discovery. The public embraced Pluto immediately, charmed by its mysterious nature and enchanted by its symbolic place on the far edge of everything familiar. Clyde Tombaugh became a celebrated figure within astronomy. His discovery was hailed as a triumph of patient observation and human dedication, and rightly so. He had done something extraordinary, not by accident, not through luck, but through countless hours of disciplined, careful work. His story stood as a reminder that science often advances not in leaps and bursts, but in the quiet, steady progress of people willing to look closely at what others might overlook. Pluto earned its place in the solar system not because it fit neatly into a definition or matched someone's expectations, but because it was real. It moved. It existed where someone had once only guessed, and it took the skill and determination of a young astronomer to bring it out of the darkness. Pluto's discovery remains one of the most human moments in modern astronomy, born not from advanced technology, but from persistence, curiosity, and the willingness to stare at thousands of silent stars until a single one finally moved. Pluto entered the solar system's story wearing a much larger coat than it deserved. When Clyde Tombaugh first revealed the faint moving dot on his photographic plates, astronomers naturally assumed it must be big. In those early months of 1930, there was very little information to work with. Pluto was too distant to appear as anything more than a speck of light, and that speck did not give away its size. So astronomers fell back on the assumptions built from the earlier search for Planet X, the hypothetical world Percival Lowell believed was causing subtle disturbances in the orbits of Uranus and Neptune. If that unseen world was massive enough to tug on giant planets, surely the object Tombaugh had found must be large. Many imagine Pluto as something close to Earth in scale, perhaps even larger than Mars. Newspapers printed diagrams of the solar system showing a ninth planet nearly as big as Earth, drifting majestically beyond Neptune. The idea captured the public imagination. People liked the thought of a substantial new world waiting out in the cold, something grand and important added to the cosmic family. It gave a sense of symmetry to the solar system. 4 rocky planets, 4 gas giants, and one more planet occupying the distant frontier. Pluto seemed to balance the arrangement, giving the solar system a neat sense of completion. But the truth was that astronomers had almost no evidence to support these early guesses. They were basing Pluto's supposed size on expectation rather than measurement. As telescopes improved through the 1930s, astronomers tried to estimate Pluto's size using brightness. But this method was tricky, because brightness does not only depend on size, it also depends on reflectivity. A small object coated in bright reflective ice can appear just as luminous as a much larger, darker object. Without knowing Pluto's surface composition, early calculations drifted wildly. Some astronomers estimated that Pluto was roughly the size of Earth's moon. Others believed it might be even bigger. Each new measurement seemed to shrink Pluto further, but no one could agree by how much. By the 1950s, evidence was mounting that Pluto was not the enormous Planet X people once imagined. Observations of Neptune's orbit improved, and astronomers realized that many of the irregularities Lowell had noticed were caused by errors in the data, not by the presence of another massive world. The need for a large, unseen planet diminished. Pluto no longer required the mass that Lowell had attributed to it, but the scientific community still lacked the tools to measure its true size directly. Pluto remained a faint spot, stubbornly refusing to reveal more than the slightest details. What puzzled astronomers most was Pluto's faintness. If it truly were a world much larger than Earth's moon, it should have reflected enough sunlight to appear brighter in their telescopes. Instead, Pluto was barely visible at all, glowing as a soft pinpoint that often seemed on the verge of disappearing. Some astronomers wondered if its surface was unusually dark, coated in materials that absorbed most of the light. Others considered the possibility that Pluto's orbit carried it into dusty regions that obscured its true brightness. The explanations grew increasingly creative because Pluto refused to align with any of the expected patterns. Then something significant happened in 1978. While studying Pluto through a telescope at the United States Naval Observatory, astronomer James Christie noticed an odd bump on one of the images. It appeared, disappeared, and reappeared over several days. After checking carefully, he realized the bump was a moon, Pluto's first known companion, later named Charon. The discovery of Charon changed everything. By studying the orbital dance between Pluto and its moon, astronomers could finally calculate Pluto's mass with accuracy. The result was astonishing. Pluto's mass was only a tiny fraction of what many had believed. It was nowhere near Earth-sized. It was not even Mars-sized. It was barely 1/5 the mass of Earth's moon. This revelation rippled through astronomy. The 9th planet, once imagined as a distant giant, had been revealed as a small icy world, lighter and far less imposing than expected. Its faintness suddenly made sense. It was not a large world with a dark surface. It was a small body reflecting limited sunlight across an immense distance. Even so, its reflectivity turned out to be higher than many imagined. Pluto was covered in bright ices, nitrogen, methane, and traces of carbon monoxide, that helped it shine more strongly than such a tiny world otherwise would. Without those ices, it might have been nearly invisible. As Pluto's true nature came into focus, astronomers began to reevaluate past assumptions. The early belief that Pluto was Earth-sized had been built on the hope of a massive Planet X. When that idea weakened, the estimates shrank. And once Charon revealed Pluto's mass, the shrinking stopped abruptly. The solar system's 9th planet was not a giant. It was a miniature. A cold, icy object with less mass than expected, a thin atmosphere and a faint glow that belied its brightness up close. Pluto had gone from imagined giant to confirmed lightweight, and it had done so over decades of careful observation. This evolution of Pluto's identity did not diminish public affection for the world. If anything, it made Pluto more intriguing. People found something endearing about a tiny planet hiding at the edge of the solar system, discovered through perseverance rather than dramatic brightness. It felt like the underdog of the solar system, punching above its weight simply by existing in a place few had expected to find it. The more astronomers learned, the more Pluto's story took shape not as a disappointment, but as a quiet revelation. What astronomers misunderstood at first was not the data itself, but the assumptions behind the data. They expected a large world because the theory of Planet X required one. They expected a certain brightness because they assumed Pluto's size matched those predictions. When reality refused to cooperate, the theories held on longer than they should have. And yet this confusion was also necessary. It drove the observations, it fueled the decades-long search, and eventually it led to one of the most interesting discoveries in modern planetary science. By the time new technologies and space missions allowed astronomers to glimpse Pluto in greater detail, the scientific community had embraced its true nature. Pluto was small, faint, cold, and distant, but it was also unique. Its surface was covered in heart-shaped plains, icy mountains and drifting hazes that no one had expected. Far from being a dull frozen remnant, Pluto turned out to be complex and surprisingly active, a world with its own character, its own history and its own secrets. Pluto's identity shifted long before anyone debated its planetary status. It went from imagined giant to misunderstood anomaly, then from anomaly to cherished world. Each stage revealed something new, peeling away old assumptions and replacing them with deeper understanding. And the further astronomers looked, the more they realized that Pluto did not need to match expectations to be extraordinary. Its mystery was never about size. It was about the quiet defiance of a world that refused to fit neatly into the categories humanity had built. All of this raises a gentle question that would guide Pluto's story for decades to come. How could such a tiny, faint world turn out to be one of the most surprising places in the entire solar system? The Kuiper Belt is a place where the solar system keeps its oldest memories. It is a region so distant and so cold that almost nothing changes quickly. Time here moves in slow, soft steps, preserving ancient materials from the very beginning of the sun's formation. When you drift into this part of the solar system, you're stepping into a kind of cosmic attic, filled with icy fragments that never grew into full planets, but never disappeared either. These frozen pieces have been circling the sun for billions of years, untouched by warmth, protected from disruption, and carrying clues to the earliest chapters of our cosmic history. To understand why the Kuiper Belt exists at all, you have to picture the solar system as it was in its infancy. In those early days, everything was chaotic. Dust, rock, gas and ice swirled around the newborn sun, colliding, clumping, and sometimes merging into larger bodies. Near the sun, the intense heat drove away lighter materials, leaving behind heavy rocky debris that eventually formed the inner planets. Farther out, where sunlight lost much of its strength, icy materials could survive. This colder zone produced the giant planets, with their thick atmospheres and massive gravitational pull. But even farther beyond them, past the orbit of Neptune, the sun's warmth weakened so much that only the coldest, most fragile materials remained. Out here, the early building blocks of planets never fully combined into a single large world. Instead, they lingered as countless small icy bodies, each one drifting through the outer darkness. These objects, some tiny, some hundreds of kilometers across, make up the Kuiper Belt. They are remnants of a time when the solar system was young, leftovers that never found a place in the grand architecture of planets and moons. Instead, they settled into slow, circular orbits around the sun, forming a wide, gentle ring of icy debris stretching from just beyond Neptune to several billion kilometers outward. For a long time, astronomers did not know this region existed. The objects were simply too faint and too distant to detect with older telescopes. Pluto was the first clue, a hint that another population of icy bodies might be hiding just beyond Neptune's orbit. It took decades before the pattern became clear. Starting in the 1990s, improved telescopes revealed object after object, confirming that Pluto was not alone at all. It was part of a vast community of distant, frozen worlds. Some were small, others surprisingly large, and all drifted through the same quiet neighborhood. This discovery reshaped our understanding of the solar system. The Kuiper Belt was not a sparse, empty region with one lonely planet at its edge. It was a teeming, ancient zone filled with icy worlds, each carrying its own story. Some of these worlds orbited neatly, others followed elongated, tilted paths. Some spun rapidly, others rotated unpredictably. The diversity of shapes, sizes and compositions suggested that the outer solar system had a far more complicated history than anyone had imagined. Within this frozen population, Pluto holds a special place. In some ways, it is entirely ordinary. It is made of rock and ice, like many other Kuiper Belt bodies. It follows a long, stretched-out orbit that sometimes brings it closer to the Sun than Neptune, but most of the time leaves it drifting in frigid darkness. It has a mixture of bright and dark regions on its surface, again common among these distant worlds. If Pluto were discovered for the first time today, it might simply join the growing list of Kuiper Belt objects, one more icy world among hundreds. Yet Pluto is also unusual. It is one of the largest bodies in the Kuiper Belt, rivaled only by a few other distant objects. It has a complex surface shaped by active processes, something rare in such cold and ancient regions. It has a thin, delicate atmosphere that expands and collapses over its orbit, a behaviour few other bodies are known to share. And it has an unusually large moon, Charon, so large that the two bodies orbit a shared centre of gravity outside Pluto itself. This makes the Pluto-Charon system behave more like a pair of partners than a planet and a moon, something unique among known Kuiper Belt objects. These characteristics set Pluto apart, transforming it from a simple icy body into a world with complex geology, chemistry, and seasonal changes. It is an example of how variety can emerge even in the coldest regions of the solar system. Many Kuiper Belt objects are little more than frozen relics, shaped mostly by collisions. Pluto, however, shows signs of internal heat, active ices, and changing landscapes. It is a reminder that distance from the Sun does not necessarily mean inactivity. Even out here, in the quiet cold, worlds can evolve. Comparing the Kuiper Belt to the asteroid belt helps make its nature clearer. The asteroid belt, located between Mars and Jupiter, is dominated by rocky fragments. These objects formed in a warmer part of the solar system and tend to be small, irregular, and heavily cratered. Collisions are relatively common there, stirred by Jupiter's gravitational influence. The Kuiper Belt, by contrast, is colder, quieter, and far less crowded. Its objects are icy rather than rocky, and many have remained unchanged since the early solar system. Collisions do happen, but they are less frequent and usually slower, allowing surfaces to remain intact for billions of years. This means the Kuiper Belt preserves ancient materials with remarkable clarity. Objects here are snapshots of the early solar system, frozen in time and kept safe from the heating, melting, and reshaping processes that affected bodies closer to the Sun. Studying them is like opening a sealed time capsule. Every crater, ridge, and patch of ice tells part of a story that stretches back to the solar system's childhood. Pluto's location makes it a natural ambassador for this region. It is bright enough and large enough to be observed in detail, yet it remains deeply connected to the icy population around it. When the New Horizons spacecraft flew past Pluto in 2015, it did not just reveal the nature of a single world, it provided insight into the entire Kuiper Belt. The mountains of water ice, the flowing nitrogen plains, the delicate atmospheric haze, and the unusual variety of surface colours were clues pointing to the processes shaping far more distant bodies. The quiet environment Pluto inhabits shapes everything about it. Temperatures remain low enough for exotic ices to stay solid. Sunlight is too weak to drive rapid change, so landscapes evolve slowly. The vacuum is too thin to scatter sound, leaving the region almost entirely silent. Even time behaves differently here. A single orbit around the Sun takes Pluto almost 248 Earth years, meaning a season lasts longer than a human lifetime. The pace of existence is slow, steady, and serene. In this ancient environment, Pluto is both a representative and an outlier. It shares the Kuiper Belt's icy origins and distant orbit, yet it defies expectations by being more dynamic and complex than other bodies nearby. Its heart-shaped plain, rising mountains, drifting glaciers, and shifting atmosphere reveal a world that remains active despite the extreme conditions. This dual identity, ordinary in some ways, extraordinary in others, makes Pluto one of the most intriguing members of its vast frozen community. It is a world shaped by the Kuiper Belt, yet capable of surprising even the scientists who study the region most closely. And as the quiet debris of the early solar system continues its slow journey around the Sun, one question begins to form about Pluto's place in this ancient environment. How did such a small, icy world manage to develop such an astonishingly detailed and dynamic surface in a region that has barely changed for billions of years? Pluto's surface looks at first like a quiet patchwork quilt stitched together from light and shadow. When you see it from a distance, the world appears mottled and uneven, a mixture of bright areas that shine like frost in morning light, and darker regions that resemble soot brushed across ice. This patchiness puzzled astronomers long before spacecraft ever visited Pluto. Through early telescopes, Pluto was little more than a fuzzy dot, but careful observers noticed the way its brightness seemed to shift slightly as it rotated. Something on its surface was changing from light to dark, dark to light, giving it a strangely uneven appearance that hinted at a world far more complex than anyone expected. For decades, astronomers could only imagine what caused these variations. Some suspected that Pluto might have enormous polar caps made of frozen gases, expanding and shrinking as the seasons crawled across its distant orbit. Others proposed dark regions created by ancient impacts or deposits of organic molecules. Without close-up images, the guesses drifted between science and speculation. It was not until the New Horizons spacecraft approached Pluto in 2015 that the mottled, patchy face of this distant world finally came into focus. What appeared was a landscape of remarkable contrast. Pluto's bright regions gleamed almost white, made from reflective ices containing nitrogen, methane, and carbon monoxide. These exotic substances behave like water does on Earth, freezing and thawing in slow cycles governed by sunlight, shadow, and seasonal change. But because Pluto is so cold, these ices remain solid at temperatures hundreds of degrees below freezing, forming shimmering plains and smooth sheets that stretch across kilometers of terrain. The darker regions, by contrast, are coated with complex organic materials formed when sunlight interacts with methane. These molecules accumulate over time, creating broad patches of reddish-brown color that stand out sharply against the surrounding ice. The balance between these bright and dark areas gives Pluto its unmistakable appearance. One hemisphere shines with the enormous heart-shaped plain of Sputnik Planitia, while the other is marked by areas so dark they almost seem to drink in what little sunlight reaches the world. These dark patches are not uniform. They form bands, streaks, and shapes that look almost painterly, as though nature brushed them onto the surface with a careful hand. Some of the darkest regions appear near Pluto's equator, while lighter zones gather around the poles, but the distribution is far from symmetrical. Pluto's face is a mosaic created by chemistry, climate, and time. Even the bright regions reveal surprising complexity when viewed up close. Water ice forms the bedrock of Pluto's surface, harder than granite at such low temperatures, and it rises into mountains and ridges. But on top of this solid foundation lie sheets of nitrogen and methane ice, which behave almost like thick frozen snow. These layers can flow slowly, pulled by gravity and shaped by the gentle cycles of sublimation and deposition. In some locations, the ice smooths the landscape into gentle curves. In others, It breaks into polygon-shaped patterns that resemble cracked mud or dragon scales, each piece formed by the slow expansion and contraction of the surface over time. Scientists had never seen anything like it. Before New Horizons, many believed Pluto would resemble a frozen cratered sphere, not so different from some of the moons orbiting the giant planets. They imagined an ancient inactive surface, cold and unchanged for millions of years. But Pluto defied those expectations. Instead of a battered relic, it revealed vast plains with almost no craters at all, regions so young that surface features must be renewed by internal processes. This was unexpected for such a small world. Heat should have escaped long ago, leaving Pluto geologically silent. Yet the patterns on its surface told a different story. The mottled appearance also reflects the slow dance of Pluto's atmosphere. Although thin and delicate, this atmosphere plays a crucial role in shaping the surface below. When sunlight reaches Pluto, even in its weakened state, it warms the surface, enough for some of the nitrogen and methane ice to sublimate into gas. When Pluto rotates and temperatures drop, that gas refreezes elsewhere, creating shifting patterns of frost and ice across the landscape. Over years and decades, this behavior refreshes some regions while leaving others untouched. It is as if Pluto wears seasonal coats of frost that slowly rearrange themselves over time, producing an ever-changing pattern of brightness. Carbon monoxide ice is found in smaller amounts, but it contributes to the shimmering quality of Pluto's surface. Its presence affects how sunlight reflects off certain areas, sometimes brightening patches and giving them a frosty glow. Water ice, being darker and less reflective, forms the underlying shapes. Methane ice brightens the higher areas, while nitrogen ice fills the low-lying basins with wide, luminous sweeps. The interplay of these materials creates a world where brightness and darkness are not simply random patches, but clues to processes that continue shaping the surface despite the intense cold. Pluto's dark regions, meanwhile, carry their own story. These areas are rich in tholins, complex organic molecules formed when ultraviolet light interacts with methane. Over long periods, these materials accumulate, giving parts of Pluto a reddish cast. The degree of darkness depends on how long the surface has been exposed to sunlight without being resurfaced by fresh ice. A dark patch might indicate an ancient area left untouched for eons, while a lighter region may have been more recently refreshed. This adds a sense of time to Pluto's appearance. Its mottled face is not just a snapshot, it is a record of history written in light and shadow. One of the most intriguing aspects of Pluto's appearance is the variety of textures found across its surface. Some regions look smooth and soft, while others appear rugged or fractured. Certain areas resemble shattered glass, with ridges and troughs slicing across the plains. Others look like dunes or windswept deserts, although no wind strong enough to create such shapes exist here. Instead, subtle processes, freezing, sublimation, and the slow movement of ice, create patterns that mimic behaviors seen on Earth, Mars, and icy moons, yet with entirely different mechanisms behind them. Early guesses about Pluto's appearance were understandably limited. Astronomers imagined a simple, icy sphere, perhaps with a few craters and slight variations in colour. The reality turned out to be far more beautiful. Pluto's surface is a quiet catalogue of processes that are both familiar and alien. It is shaped by chemistry that thrives in extreme cold, by sunlight that arrives as a pale flicker, and by internal interactions that no one expected such a small world to maintain. Modern understanding paints Pluto as a world of contrasts, where bright plains stretch beside ancient shadows, where icy cliffs rise beside smooth frozen lakes, and where colours range from pale white to deep rust. Its surface patterns are not static. They are snapshots of ongoing interactions between frost, atmosphere, temperature and time. Pluto's frozen face is not a mask of stillness, but a dynamic landscape that quietly evolves in the darkness. What stands out most is how expressive this distant world appears. Its mottled surface feels almost like a personality, a mixture of soft brightness and quiet shadow. It is a reminder that even in the coldest corners of the solar system, nature finds ways to create complexity, surprise, and subtle beauty. And after seeing the way Pluto's icy face blends brightness and darkness into a single, intricate tapestry, a question naturally appears like a whisper across the frozen plains. What hidden forces shaped these patterns into the portrait we see today? Sputnik Planitia is the feature that made Pluto instantly recognizable, even to people who had never given much thought to the outer solar system. When the New Horizons spacecraft sent back its first high-resolution images in 2015, the world saw a bright, smooth, heart-shaped plain spread across one side of Pluto's surface. It was unexpected, unmistakable, and oddly touching. In a place so distant and so cold, where sunlight is barely strong enough to cast a shadow, a natural heart appeared in the ice. But beneath that gentle shape lies one of the most scientifically important landscapes in the entire outer solar system, a place where exotic ices move, shift, and breathe in ways that defy expectations for such a small frozen world. Sputnik Planitia is made mostly of nitrogen ice, mixed with smaller amounts of methane and carbon monoxide. On Earth, nitrogen is an invisible gas that forms most of the air you breathe. On Pluto, where temperatures fall to levels that make even oxygen freeze solid, nitrogen becomes a pale, silky sheet that coats the surface like frozen cream. This nitrogen ice is soft compared to the rock-hard water ice that forms Pluto's mountains. It can flow slowly, stretch across basins, and rise again like a sluggish glacier. The bright whiteness of the plain comes from the reflective nature of fresh nitrogen frost, which gleams beneath Pluto's dim sunlight and makes this basin stand out dramatically from the darker regions around it. The heart shape, though striking, is only part of the story. Sputnik Planitia itself is a giant impact basin, a deep depression where a long-ago collision carved a vast hollow in Pluto's crust. Over time, nitrogen ice filled this basin, creating a smooth surface almost entirely free of craters. This lack of cratering was one of the most surprising discoveries. On most ancient worlds, craters are everywhere. They accumulate over billions of years, marking every collision that has taken place in the solar system's long and restless history. But Sputnik Planitia is different. Its surface is so young, so frequently refreshed, that old craters have been erased. This means the nitrogen ice here is in motion, resurfacing the plain and smoothing out imperfections. The glacial activity sweeping across Sputnik Planitia is one of the most astonishing behaviors seen on Pluto. Despite the incredibly low temperatures, nitrogen ice can behave as a slow, heavy fluid. Under the pull of gravity, it creeps outward from the center of the basin toward its edges, flowing around obstacles and carving pathways into the surrounding terrain. Patterns seen on the plain, polygon shapes resembling cracked mud, long troughs and curved ridges, suggest that this ice rises and falls on timescales of thousands or millions of years. Heat escaping from Pluto's interior may warm the bottom of the nitrogen layer slightly, helping it glide over the water ice crust beneath. In this way, Sputnik Planitia acts almost like a frozen sea, with currents that move so slowly they become almost geological rather than seasonal. The presence of this much nitrogen ice has a powerful effect on Pluto's rotation. Sputnik Planitia is enormous, roughly the size of a continent on Earth, and because nitrogen ice is less dense than water ice, the basin behaves like a giant weight imbalance on Pluto's surface. Imagine spinning a ball with a slightly heavy patch on one side. Over time, the heavy patch would tend to drift downward, pulling itself into a position of stability. Pluto behaves similarly. The presence of the thick nitrogen ice plain has gradually shifted Pluto's orientation, so that Sputnik Planitia now faces almost directly opposite Charon, Pluto's largest moon. This arrangement is not accidental. Pluto and Charon are locked in a gravitational partnership where each keeps the same face turned toward the other, and the weight of Sputnik Planitia helped Pluto settle into its current stable configuration. This effect, called true polar wander, suggests that Pluto's crust may be decoupled from its interior, meaning the outer shell of the world can shift or rotate independently from deeper layers. This behavior is difficult to explain unless Pluto has a subsurface ocean, or at least a layer of partially softened material beneath the crust. In other words, Sputnik Planitia may be indirect evidence that Pluto once held, or may still hold, an underground ocean. The idea that a tiny distant world, frozen at the edge of the solar system, could hide liquid water beneath its icy crust is one of the reasons scientists find Pluto so endlessly fascinating. The plain itself is also a dynamic part of Pluto's climate. As Pluto orbits the Sun over the course of nearly 250 Earth years, the amount of sunlight reaching its surface changes slightly. Even that small shift is enough to make nitrogen frost sublimate into gas during the warmer decades and freeze back onto the ground during the colder phases. Over time, this process transfers nitrogen between the poles and Sputnik Planitia, constantly refreshing the plain and contributing to its bright appearance. Fresh nitrogen frost reflects light more effectively than older, darker surface materials, helping Sputnik Planitia keep its distinctive pale glow. Patterns etched into the plain reveal even more about its activity. The polygon shapes seen across much of Sputnik Planitia resemble convection cells, structures that form when warmer material rises and cooler material sinks. On Earth, convection is seen in boiling water or rising air currents. On Pluto, it may exist deep within the nitrogen ice, where slightly warmer material rises slowly while colder material sinks. Each cell can span tens of kilometers, creating a vast mosaic across the plain. This kind of convection has never been seen before on such a small, icy world, and it suggests that Pluto's internal heat still influences the surface today. Dark streaks near the edges of the plain hint at winds gently blowing across the basin, carrying particles of tholin and other organic materials and depositing them in faint trails. Although Pluto's atmosphere is thin, it is capable of moving tiny particles across large distances over long periods. These streaks add another layer of texture to the plain, emphasizing that even in a place with almost no weather, subtle processes shape the surface. Sputnik Planitia also acts as a kind of climate engine for Pluto. Because nitrogen is the main component of Pluto's atmosphere, the plain plays a key role in regulating atmospheric pressure. When nitrogen frost sublimates, the atmosphere grows thicker. When it freezes, the atmosphere thins. In this way, the plain breathes over long timescales, helping Pluto maintain an atmosphere despite its extreme distance from the Sun. Before New Horizons, scientists had only the faintest idea of what this region might contain. Some suspected it might be a bright polar cap, others imagined a smooth icy field, but nothing prepared them for the sight of an enormous heart-shaped basin with active glacial processes and a surface so young it looked freshly laid. Sputnik Planitia forced scientists to rethink much of what they believed about small icy worlds. It showed that even tiny planets can be alive with internal heat, surface renewal, and slow but powerful geological activity. The scientific importance of Sputnik Planitia goes beyond Pluto. It challenges long-standing assumptions about how worlds cool, how they evolve, and how they store heat. It suggests that exotic ices can flow and shift in ways similar to glaciers on Earth, even at temperatures far colder than anything found here. It also hints that subsurface oceans may be more common than previously imagined, potentially increasing the number of worlds in the solar system that could have once supported life. Yet despite all its scientific significance, the plane still carries its gentle, iconic shape. It remains a symbol of Pluto itself, bright, surprising, quietly powerful, and shaped by forces working far beneath the surface. After all the measurements, theories, and discoveries, its appearance still resonates emotionally, a heart carved into the ice at the very edge of the solar system. And every time you look at that distant frozen heart, a thought rises softly in the background. What kind of world beats quietly beneath the surface of such an impossibly cold and fragile sea of ice? The mountains on Pluto look like something sculpted from another universe, tall and jagged, rising out of the frozen plains with a kind of quiet defiance. At first glance, they resemble the rocky ranges found on Earth or Mars, with steep slopes, sharp peaks, and shadowed valleys. But these peaks are not made of rock. They are made of water ice, ordinary water, the same substance that pours from taps and falls as rain back home. The difference is the temperature. On Pluto, water ice becomes so cold that it behaves more like solid stone than frozen liquid. Its structure locks into a hardness that rivals granite, allowing it to form towering mountains in a landscape where almost everything else lies smoothed and softened by exotic ices. To understand why these mountains stand so tall, you have to imagine what happens to water when it is chilled to the extreme. On Earth, ice melts and flows easily, collapsing under its own weight and slowly creeping downhill. But on Pluto, where temperatures fall to around -200 degrees Celsius, water ice becomes rigid and immovable. At such cold levels, the molecules inside the ice vibrate only faintly, forming a structure that resists deformation. A block of water ice at Pluto's temperature would feel harder than sandstone, tougher than many kinds of bedrock. If you tried to strike it with a hammer, the hammer would bounce back with a jolt. This extraordinary hardness gives Pluto's mountains the strength to rise kilometers above the surrounding plains without crumbling or sagging under their own weight. The highest of these ranges include Norgay Montes and Hillary Montes, named to honor the climbers who conquered Earth's tallest peak. These mountains reach heights of more than 3 kilometers, towering above the icy plains of Sputnik Planitia. Seen from above, they appear as dark, rugged islands surrounded by a sea of bright nitrogen ice. Their sharp peaks cast long shadows across the frozen landscape, emphasizing their height against the smooth expanses around them. Unlike Earth's mountains, which are shaped by plate tectonics as seismic activity and erosion, Pluto's mountains owe their existence to a very different set of geological forces. On Earth, Mountains form where continents collide, pushing rock upward over millions of years. But Pluto has no shifting plates, no continents grinding against one another, and no thick atmosphere to erode surfaces through wind and rain. Instead, its mountains likely formed when blocks of water ice bedrock were uplifted by underlying forces, perhaps the slow movement of material beneath Pluto's crust, or the long-ago impacts that created deep basins. Some mountains may have formed when fractures opened in Pluto's crust, causing large slabs of water ice to rise like frozen pillars. Others may be remnants of ancient ridges or cliffs, preserved in the extreme cold. Because water ice behaves like rock on Pluto, it can hold steep shapes for billions of years. Slopes remain sharp instead of crumbling into rubble. Peaks remain pointed instead of being worn down by the elements. With no liquid water to carve valleys, no atmosphere dense enough to carry dust or snow, and no rapid changes in temperature to fracture the ice, Pluto's mountains keep their forms almost perfectly. They stand as monuments to the processes that built them, unchanged except for the faint dusting of organic particles carried by the thin atmosphere. Despite their harshness, these mountains create a sense of beauty on Pluto. Their color is darker than the plains around them, revealing the underlying water ice that forms the foundation of the world. Many peaks appear bluish when captured by New Horizons, a hint at the chemical properties of the ice itself. Some look streaked or layered, suggesting sculpting by long-gone geological events, and all of them cast deep, crisp shadows that stretch far across the ground in the dim Plutonian light. The contrast between Pluto's mountains and its surrounding plains is striking. Sputnik Planitia, made of nitrogen ice, is soft, smooth, and constantly reshaping itself through glacial flow. Water ice mountains, by contrast, are rigid and eternal. They rise out of the plain like islands caught in the middle of a frozen ocean. Nitrogen ice flows around them, creeping into valleys and pooling in basins, but never eroding the mountains themselves. It is as though Pluto's landscape is divided into two realms, one fluid and changing, the other ancient and steadfast. From above, these mountains appear almost misplaced, as though some unseen force pressed Earth-like features into an otherworldly environment. But they make perfect sense once you understand the roles different ices play on Pluto. Water ice forms the skeleton of the world, the strong supportive layer beneath everything else. Nitrogen, methane, and carbon monoxide form the soft outer skin, shifting in response to sunlight and seasonal changes. Together, these materials create a world where mountains and plains coexist through a delicate balance of strength and softness. Mountains on Pluto also reveal clues about its internal structure. Their height suggests that Pluto has enough internal heat to allow slight movement beneath its crust. If the crust were completely rigid and frozen solid to great depths, mountain building would be extremely limited. But the presence of tall peaks implies that some parts of the crust were once flexible enough to shift, uplift, or fracture. This supports the idea that Pluto may have a subsurface ocean, or at least a layer of partially softened material beneath the hard, icy shell. One of the most evocative aspects of these mountains is the stillness that surrounds them. On Earth, mountains are alive with sound, wind whistling across ridges, snow tumbling down slopes, and rivers carving paths through valleys. On Pluto, silence dominates. The atmosphere is too thin to carry sound in any meaningful way. A stone falling from a cliff would land without a single echo. A person standing at the foot of one of these icy mountains would hear nothing but their own breath, quiet and rhythmic beneath the endless darkness of the sky. Even light takes on a different texture here. Shadows deepen into near black shapes, sharply defined by the distant sun. This frozen stillness gives Pluto's mountains a kind of ancient dignity. They do not change quickly, they do not crumble or shift, they endure. They stand as reminders that geology does not always need heat or plate tectonics to produce grandeur. Sometimes, extreme cold is enough to sculpt a landscape of astonishing scale and beauty. And yet, despite their silence and strength, these mountains raise a gentle question. How did such towering structures form in a world so small, so cold, and so far removed from the forces that shape mountains on Earth? The glaciers on Pluto move so slowly that, if you stood beside one, you would never notice the motion. You could wait an hour, a day, an entire human lifetime, and the landscape would look unchanged. But over centuries and millennia, the nitrogen ice that fills Pluto's Great Plains does something remarkable. It flows, it creeps, it travels across the surface in a slow, steady drift, driven by sunlight so faint it barely warms the ground, and by temperature changes so subtle they unfold over decades. In a world this cold, this distant, and this dimly lit, the idea of glaciers in motion feels almost impossible, and yet they move all the same, revealing a quiet type of activity that continues even in the deep outer dark. Nitrogen behaves very differently on Pluto than it does on Earth. Here at home, nitrogen is a gas, invisible and weightless, making up most of the air we breathe. But on Pluto, where temperatures regularly drop below -200 degrees Celsius, nitrogen settles into a solid state. It freezes into a smooth, pale ice that is much softer than the rock-hard water ice forming Pluto's mountains. This softness is key. Under pressure, nitrogen ice can deform, stretch, and glide, much like thick snow slowly sliding down a slope. Where water ice gives Pluto its tall, jagged peaks, nitrogen ice fills the lowlands like a flowing blanket. Sputnik Planitia, the enormous heart-shaped basin, is the center of this activity. Its surface may look smooth and peaceful, but beneath that calm exterior, nitrogen ice is constantly shifting. Slight differences in thickness, temperature, and sunlight drive movement across the plain, causing the ice to push outward from the center and creep toward the surrounding terrain. The result is a vast, frozen sea of slow motion, where the waves unfold over geological timescales rather than seconds. The primary engine behind this movement is sublimation, the process where frozen nitrogen turns directly into gas without passing through a liquid stage. When sunlight reaches the surface, even in the gentlest touch, it warms the nitrogen ice just enough for some of it to sublimate. This gas then escapes into Pluto's thin atmosphere. When the temperature cools again, usually during long nights or in shadowed regions, that same nitrogen refreezes. Over time, this cycle of sublimation and refreezing transfers material across the landscape. It builds up in some areas and erodes away from others, nudging the glaciers forward in a slow, steady drift. Think of it like breathing. During warmer phases, the surface exhales nitrogen gas. During colder phases, it inhales frost. This rhythmic exchange gives Pluto's glaciers a strange vitality. They shift, stretch, and reshape themselves in ways more reminiscent of living systems than frozen deserts. Even though the pace is unimaginably slow, the movement is real, and it leaves signatures across the surface that New Horizons captured in striking detail. One of the most fascinating patterns created by these glaciers is the vast network of polygon-shaped cells etched into the surface of Sputnik Planitia. These huge geometric shapes, some dozens of kilometers across, resemble the patterns found in drying mud or cooling lava. But on Pluto, they may be the result of convection within the nitrogen ice. Beneath the plane, slightly warmer ice rises, while cooler ice sinks, creating a slow, churning motion that pushes the surface upward in repeating polygons. Each cell becomes a frozen bubble of upward force, bordered by troughs where the ice sinks back down. The cells shift over time, yet their outlines remain crisp and distinct, giving the plane its signature textured appearance. The troughs that outline these polygons reveal the direction of glacial flow. Nitrogen ice slowly migrates outward from the centers of the cells, flowing toward the edges and creating subtle cracks that run like seams between the polygons. These troughs can reach depths of several tens of meters, standing out as dark lines against the brighter ice. They are the marks of movement, tiny signatures of a world where glaciers glide slowly across a frozen sea. Pluto's weak gravity also plays an important role in shaping these glaciers. With gravity only a fraction of Earth's, nitrogen ice does not feel the same pressure to collapse or flatten. It can stack, stretch, and mound without being forced into a flat layer. This allows glaciers to build up significant thickness, forming deep reservoirs of ice that can flow for long distances. It also helps maintain the dramatic height contrasts between Sputnik Planitia's smooth basin and the towering mountains that surround it. The nitrogen ice is heavy enough to move, but light enough to be easily shaped by temperature and subtle internal heat. Weak gravity also means that glacial movement on Pluto is gentle, wide, and slow. Instead of carving deep valleys or forming sharp creases, the glaciers leave broad, smooth pathways. As the nitrogen ice flows, it carries dark particles, organic molecules and dust along with it. These materials sometimes gather in streaks or pools, leaving faint dark smudges across the bright plane. These patterns, though subtle, show the direction and behavior of the flow, giving scientists clues about how the glacier has moved over time. One of the surprising discoveries from New Horizons was how young many of these glacial features appear. Some portions of Sputnik Planitia have surfaces less than 10 million years old. In geological terms, that is incredibly recent, almost newborn. It means the glaciers are not relics from Pluto's distant past, but active participants in shaping the world today. They renew the surface, erase craters, fill depressions, and reshape boundaries. Even in a place where the sun is barely a bright dot in the sky, the climate is still capable of driving cycles of ice and frost. This activity raises an interesting question. Where does Pluto get the energy to move these glaciers at all? The answer is subtle. Even a tiny amount of heat from Pluto's interior, perhaps left over from its formation or generated by radioactive elements in the core, can create temperature differences in the thick nitrogen ice. These small variations, spread over vast distances, are enough to set the glaciers into motion. Sublimation, refreezing, and internal heat come together to create a delicate balance that fuels Pluto's slow but persistent geologic activity. There is something calming about this kind of movement. It is patient, it is measured, it unfolds in silence beneath a sky so dark that stars shine all day long. The glaciers on Pluto do not roar, crack, or collapse like glaciers on Earth. They drift quietly, almost thoughtfully, as though the landscape is taking its time to decide where everything should go. The frozen surface breathes, stretches, and settles, leaving behind patterns that are both elegant and ancient. Seen in this light, Pluto's glaciers become a reminder that not all worlds require warmth to be dynamic. Even in the deep cold, where sunlight is faint and temperatures plunge to levels unimaginable on Earth, motion persists. Change continues. Pluto is not a frozen relic locked in stillness. It is a world shaped by slow rhythms, subtle forces, and patient geological processes that have been active for millions of years. And as you picture those glaciers creeping gently across the plains of Sputnik Planitia, barely noticeable yet endlessly persistent, a quiet question rises from the cold. What deeper mysteries lie beneath the surface of a world that moves this slowly, yet never truly sleeps? Pluto's atmosphere is so thin and delicate that you could walk through it without feeling the slightest resistance. It presses down with a force far weaker than even the highest mountain air on Earth. And yet, despite its frailty, this atmosphere creates one of the most unexpectedly beautiful sights in the outer solar system. It is made mostly of nitrogen, with a sprinkling of methane and a trace amounts of other gases. These ingredients drift above Pluto's surface in gentle layers, forming an atmosphere that changes slowly with the seasons and glows with the soft blue light when the distant sun shines through it at just the right angle. It is faint, fragile, and easy to miss. But it gives Pluto a quiet elegance that no one expected to find this far from warmth. The atmosphere begins at the surface, where frozen nitrogen lies scattered in plains, patches, and layered deposits. During the slightly warmer phase of Pluto's long orbit, sunlight, weak as it is, touches the surface with enough energy to make some of that nitrogen sublimate. It slips directly from solid to gas, rising into the air like an exhale so soft it is almost metaphorical. Methane behaves similarly, lifting into the sky and mixing with nitrogen to form the thin atmospheric envelope that surrounds the world. The rising gas is spread out, forming a gentle pressure that clings lightly to the planet, only a whisper of an atmosphere, but enough to create fascinating behavior. One of the most striking discoveries made by the New Horizons spacecraft was that Pluto's atmosphere is layered with haze, dozens of thin, delicate sheets rising high above the surface. These haze layers are not uniform. They form stacked bands, sometimes separated by tens of kilometers, each one drifting like gauzy curtains suspended in the thin air. The layers appear bluish when sunlight passes through them, giving Pluto an unexpected halo of color. It is a remarkable sight for a world so cold and distant that one might expect nothing more than a faint glow. The haze forms when methane in Pluto's atmosphere rises high enough to be broken apart by sunlight. Even the dim light of the sun, arriving from billions of kilometers away, carries enough energy to split methane molecules. When this happens, the fragments recombine into more complex hydrocarbons, tiny particles that cling together and slowly settle downward. These particles scatter light in a way that creates the blue glow captured in the New Horizons photographs. The effect is surprisingly similar to the way Earth's sky looks blue, although the mechanisms differ slightly. On Earth, nitrogen scatters sunlight. On Pluto, the scattering comes from tiny suspended particles created by chemistry in the upper atmosphere. What makes Pluto's haze layers even more mesmerizing is how far they extend upward. Some stretch more than 200 kilometers above the surface, an enormous height for such a small world. And the layering suggests that Pluto's atmosphere is shaped by waves, gentle rising and falling motions like ripples in a slow-motion sea. These atmospheric waves can lift particles, create boundaries, and form the distinct tiers seen from orbit. The result is a glowing envelope that looks almost delicate enough to vanish at a breath. But Pluto's atmosphere does not remain constant. It thickens and thins dramatically over the course of its long orbit around the Sun. During the years when Pluto drifts closer to the Sun, more nitrogen and methane warm enough to sublimate from the surface. The atmosphere grows thicker, though thicker is a relative term. It is still incredibly faint compared with Earth's. When Pluto moves farther away again and winter arrives, the opposite happens. Temperatures drop, the feeble sunlight weakens further, and the atmosphere begins to collapse. Gases freeze out of the air and settle gently onto the ground as frost, building layers that lie in wait until the seasons shift once more. This cycle of freezing and sublimation gives Pluto's atmosphere a slow pulse. Over decades and centuries, the atmosphere breathes in and out, expanding and contracting with the rhythm of its orbit. When nitrogen gas freezes and falls back to the surface, it lands quietly as a thin coating of frost. Over years, this frost can accumulate, altering the brightness of certain regions and contributing to the mottled appearance of Pluto's face. In some places, frost collects more thickly, brightening the landscape. In others, it sublimates away, revealing darker patches rich in organic molecules. The behavior of methane adds another layer to this atmospheric story. Methane does not freeze as readily as nitrogen at Pluto's temperatures, so it persists in the atmosphere even when nitrogen begins to fall as frost. This creates a delicate balance between the two gases. Methane influences the temperature of the atmosphere, trapping a small amount of heat and helping maintain the conditions needed for haze to form. Methane also contributes to the chemical reactions that produce complex hydrocarbons, giving Pluto's haze its distinctive colour and feeding the slow drift of particles that eventually settle on the surface as a reddish dust. One of the most fascinating aspects of Pluto's atmosphere is how it interacts with the surface in subtle, graceful ways. During the warmer decades, when the atmosphere is present and pressure rises slightly, winds may form, gentle breezes that carry fine particles across the plains. These winds are not strong enough to howl or carve dramatic dunes, but over long periods they can shape faint streaks and deposits along the ground. Some of the dark lines seen around Sputnik Planitia may be the result of particles blown into shallow ridges or collected in wind-protected corners. Even more surprising is how sunlight affects the atmosphere near the surface. When the sun is low on the horizon during sunrise or sunset, the atmosphere glows brightly in a halo of blue light. This halo was captured beautifully by New Horizons as it looked back toward Pluto, showing the world rimmed with an ethereal ring that no one expected. The glow is caused by the scattering of light through the haze particles and the thin mixture of gases that cling to the world. The result is a dreamy, almost magical sight, a small distant world shining with a colour that feels familiar, even comforting. Although Pluto's atmosphere may someday vanish entirely as temperatures drop during the farthest reaches of its orbit, it will likely return when the world swings back into slightly warmer sunlight again. This cycle makes Pluto unusual. Few places in the solar system have atmospheres that appear and disappear in such long, graceful rhythms. Most worlds either hold on to their atmospheres or lose them permanently. Pluto lives somewhere between those extremes, keeping an atmosphere that waxes and wanes like a distant breath. This fragile sky teaches scientists a great deal about how atmospheres behave in extreme conditions. It shows that even weak sunlight can drive surprising chemical reactions. It demonstrates that a world does not need strong gravity or warm temperatures to maintain a dynamic atmosphere. and it highlights how delicate interactions between surface and sky can shape a world over time, even when that world is almost too cold for molecular motion. Pluto's atmosphere, with its soft haze and gentle blue glow, is a reminder that beauty can emerge in the most unlikely places. It drifts above a frozen landscape, subtle and temporary, yet rich with scientific clues and quiet wonder. And as you picture that faint shimmering halo stretching above Pluto's plains, you might find yourself wondering something simple yet profound. How does such a delicate veil of gas survive in a place where even sunlight arrives as little more than a whisper from across the void? Pluto's seasons unfold so slowly that they feel almost detached from time itself. On Earth, the movement of seasons is familiar and reassuring. Leaves brighten, then fall. Days shorten, then lengthen. Winter gives way to spring with a kind of steady rhythm. But on Pluto, that rhythm is stretched so far that an entire human lifetime fits comfortably inside a single season. The causes lie in two deep, defining features of Pluto's identity: its extreme axial tilt and its long stretched-out orbit. Together, they create a world where sunlight drifts across the surface in slow, wandering arcs, taking decades to shift from one hemisphere to the other. Time here does not feel rushed. It does not feel urgent. It feels like a gentle unfolding, a tide that moves at the speed of generations. Pluto's tilt is extraordinary. While Earth tilts at a modest angle of about 23 degrees, Pluto leans dramatically at more than 100 degrees. In practical terms, Pluto is tipped so far over that it almost rolls along its orbit. For part of its long year, one pole faces the sun continuously, bathing that region in weak, steady daylight for decades. The other pole sits in darkness just as long, held in a deep, cold night that lasts longer than most human lifespans. Later, the orientation reverses, and the poles trade places, swapping their roles as keeper of the light and guardian of the dark. This tilt alone would create unusual seasons, but Pluto's orbit amplifies the effect. Rather than circling the sun in a nearly round path like Earth, Pluto follows an elongated ellipse, sometimes drawing closer to the sun and sometimes drifting far beyond the reach of meaningful warmth. When Pluto is at its closest point, sunlight becomes slightly stronger, still faint, but strong enough to warm certain areas and release gases from the surface. When Pluto moves to its farthest distance, the sunlight becomes so weak that the atmosphere begins to freeze. This combination of tilt and orbit means that Pluto's seasons are not just long, they are vastly uneven, shifting between times of mild activity and deep stillness. Imagine standing on Pluto's surface near the beginning of spring. The sun would hover low on the horizon, bright but small, no larger than a sparkling dot. Over days and weeks, it would rise only slightly higher, moving slowly across the sky in a gentle arc. But even after months have passed, its position would barely shift. A season on Pluto lasts roughly 60 Earth years. That means a generation can be born, grow up, and reach old age while the sun loops lazily through one portion of the sky. Children and elders would share the same season, the same light, the same faint warmth. Time becomes something felt in long, soft chapters rather than in short, sharp cycles. The slow movement of sunlight shapes every part of Pluto's environment. As regions gain light across decades, the nitrogen and methane frost that coats the surface begins to sublimate. It melts into gas without ever becoming liquid, rising into the thin atmosphere. This gradual warming builds the atmosphere over time, making it thicker and more widespread. Conversely, when sunlight moves away and long winter settles in, the opposite begins. The air cools, molecules lose energy, and the gases freeze out again. They fall softly to the ground like invisible frost, lowering the atmospheric pressure until almost nothing remains. The atmosphere breathes in and out in time with the seasons, expanding and collapsing in a cycle too slow and graceful to observe in a single human lifetime. The poles experience the most dramatic transformations. When a pole faces the sun, it receives decades of continuous daylight, never bright, but constant. During these long summers, frost recedes, gases rise, and the atmosphere flourishes. The surface brightens in patches, reflecting fresh deposits of sublimated nitrogen. As the decades progress, the pole warms just enough to change the balance of ices, revealing subtle patterns that only long-term sunlight can create. When the tilt finally shifts and the pole enters winter, darkness returns, not for months, but for generations. In that darkness, surface temperatures plunge. Nitrogen and methane fall from the atmosphere as ice, building layers that slowly thicken year after year. The world becomes quiet, the plains harden, the atmosphere thins to a whisper. These long winters are not uniform. Pluto's orbit ensures that sometimes the pole is in darkness when the world is farthest from the sun, and other times it is in darkness when Pluto is closer. This changes the depth of the freeze, it changes the thickness of the frost, it changes the behavior of the atmosphere for decades at a time. The interplay between orbit and tilt produces a world where each season carries a unique character, rather than following a simple repeating pattern. The idea that seasons can last so long brings a strange emotional depth to Pluto's story. On Earth, seasons mark the rhythm of life. They pass through quickly enough to shape memory, childhood, and the feeling of time moving forward. But on Pluto, the world feels almost timeless. A single winter could last from a great-grandparent's youth to the late years of their grandchildren. A single sunrise might mark an era rather than a moment. Daylight and darkness become slow companions that linger long enough to shape landscapes, atmospheres, and even the chemical balance of the world. This stretched passage of time also changes how scientists interpret Pluto's appearance. The shifts in brightness across its surface, the patches of frost, the dark stains of organic material, all of these are influenced by where sunlight has lingered for decades. Some regions may preserve traces of long summers, while others carry the markings of winters that lasted longer than memory. Pluto's face is not carved by daily weather, but sculpted by decades of slow change. Even the haze in Pluto's atmosphere responds to these seasonal rhythms. When sunlight touches the upper layers during warmer phases, methane breaks apart and forms the particles that create the haze. When the world cools and the atmosphere begins to freeze, the haze layers change. They thin, shift, settle, and eventually collapse as particles fall gently to the ground. These particles coat Pluto's surface in reddish dust, adding to the patchwork of colour that gives the world its unique personality. Scientists watching Pluto from afar can only glimpse tiny portions of these enormous seasonal cycles. Pluto takes nearly 248 Earth years to complete a single orbit. No single human researcher will ever see a full Plutonian year unfold. The seasons stretch too far, reaching across generations, and perhaps that is part of what makes Pluto so emotionally compelling. Its changes are not connected to human timescales. They belong to the cosmos, the slow, patient movement of worlds drifting in deep space. Pluto's seasons invite a quiet shift in perspective. They ask what time feels like when rushed days and busy weeks disappear. They ask how landscapes transform when given decades of stillness and centuries of calm. They ask what it means for a world to change so slowly that no single lifetime can witness both ends of a cycle. And as sunlight continues its gentle drift across Pluto's surface, guiding the frost, the haze, the atmosphere, and the shadows, one lingering question emerges from the deep stretch of time. How does a world stay alive and dynamic when its seasons move with the pace of eternity rather than the rhythm of days? Beneath Pluto's frozen crust, beneath the nitrogen plains and water ice mountains and slow-moving glaciers, there may be something quietly extraordinary: an ocean. Not a wide, open sea like the ones on Earth, but a hidden reservoir of liquid water sealed beneath kilometers of ice. For years, this idea sounded almost impossible. How could liquid water survive in a world so unimaginably cold, where sunlight arrives as a thin shimmer and the surface freezes harder than stone? Yet evidence gathered by the New Horizons mission and decades of careful study suggest that Pluto may indeed harbour a subsurface ocean, one kept warm not by sunlight, but by the slow heartbeat of internal heat retained over billions of years. The clues come from Pluto's surface, where cracks, ridges, and subtle tectonic features speak of forces pushing upward from below. Some of these cracks stretch for hundreds of kilometers. Their width and clean edges hint that the surface ice behaved like a shell being flexed from beneath, rather than simply breaking from external impacts. In several regions, the crust appears to have bulged, as though something below expanded or warmed enough to push outward. This kind of behavior is difficult to explain, unless there is a layer beneath the crust that can move or flow, something warmer and softer than the ice above it. One of the strongest pieces of evidence comes from Sputnik Planitia, the vast nitrogen plain that forms Pluto's heart. As the nitrogen ice filled the basin, its sheer mass would have created an imbalance in Pluto's rotation, encouraging the entire crust to shift and settle in a new orientation. This phenomenon, called true polar wander, is much easier to achieve if the outer shell is floating on a softer layer underneath. A rigid, unbroken crust would resist such movement. But Pluto appears to have reoriented itself over time, a sign that its icy shell is separated from the core by something capable of allowing rotation to decouple. A subsurface ocean fits this behavior perfectly. If Pluto does have an ocean, the question then becomes, how could liquid water remain unfrozen for billions of years in a place so cold? The answer lies in the quiet persistence of heat deep inside the world. Even small rocky bodies contain elements that release heat as they undergo radioactive decay. On larger planets, this heat is overshadowed by other sources, such as friction or core formation. But on smaller worlds like Pluto, radioactive decay becomes a slow, steady warming influence that lingers long after other heat sources fade. It is weak, but it never fully stops. This warmth, trapped beneath insulating layers of ice, may be enough to maintain a pocket of liquid water far below the surface. Pluto's crust itself also helps. It is not made of ordinary ice. At the frigid temperatures of the outer solar system, water ice becomes rigid and crystalline, forming an effective thermal blanket. Beneath that layer sits a mixture of different kinds of ices, possibly including ammonia-rich water, which lowers the freezing point. Together, these layers create a complex insulating shell. Heat from the core becomes trapped, unable to escape quickly. Over geological timescales, Even a little warmth is enough to keep the base of the ice shell melted. Cracks seen on the surface further support this idea. Some are so large that they rival continental faults on Earth. Their size suggests that Pluto's interior is expanding, perhaps as liquid water slowly freezes over time. Water expands when it freezes, pushing outward and forcing the crust to crack. This is exactly the kind of slow tectonic behavior scientists expect from a world with a gradually freezing subsurface ocean. The fractures appear fresh in many places, hinting that freezing and expansion may still be ongoing. Pluto would not be alone in having an ocean beneath a frozen exterior. Europa, one of Jupiter's moons, holds a deep ocean beneath an icy shell. Enceladus, circling Saturn, sprays plumes of water from cracks in its south polar region, proof of a subsurface sea. Triton, Neptune's largest moon, shows signs of past or present internal activity that hints at hidden water. These worlds exist in different environments, but they share a key trait with Pluto: heat retained or generated deep below the surface, protected by insulating layers of ice. Europa is warmed by tidal forces, its ocean kept liquid by the constant squeezing and flexing from Jupiter's gravity. Enceladus is similarly pulled and stretched by Saturn's powerful influence, generating internal heat. Triton likely retains residual warmth from a more complex past, possibly including capture into Neptune's orbit. Pluto, however, sits in a quieter region of the solar system, far from the intense gravitational tugging that fuels oceans elsewhere. If Pluto holds a liquid reservoir, it would mean that oceans can survive not only where gravity stirs them, but also where time, insulation, and chemistry provide the necessary warmth. This possibility changes the way scientists think about the outer solar system. It suggests that hidden oceans might be more common than previously imagined. Small, icy worlds, once assumed to be solid, throughout may hide layers of liquid water deep underground. Each of these oceans could influence the geology above it, powering tectonic movements, shaping surfaces, and altering the chemical environment in ways still being unraveled. For Pluto itself, the existence of an ocean would help explain some of its most puzzling features. It could explain why the crust seems flexible enough to move slightly over time. It could explain why certain cracks and ridges appear to have formed relatively recently. And it could explain the slow reshaping of Sputnik Planitia as nitrogen ice moves and shifts over a bed of water ice crust, supported by something warmer beneath. An ocean might even influence Pluto's rotation, helping the planet settle into its current stable configuration, with its bright heart facing opposite its moon Charon. The emotional impact of a hidden ocean beneath such a distant world is subtle but profound. There is something quietly moving about the thought that beneath the hardened exterior of a frozen dwarf planet, water might still flow. A world that seems silent and still from the outside could hide movement, warmth, and possibility deep within. The idea of an ocean beneath Pluto's surface stretches the imagination. It connects Pluto to a wider family of ocean worlds and softens the boundary between the familiar and the alien. It also raises questions about Pluto's long-term evolution. If the ocean is slowly freezing, the tectonic behavior we see today may fade in the distant future. The crust may stiffen, the cracks may cease to form, and the world may settle into a deeper stillness. But if the ocean is maintained by insulating layers and chemical mixtures that keep it liquid, then Pluto may continue quietly shaping itself for billions of years to come. This ocean, if it exists, is not the warm, bright sea of storybooks. It would lie in darkness, without light or waves, sealed beneath layers thicker than mountains, but its existence would make Pluto one of the most surprising places in the solar system. A world that challenges assumptions simply by hiding something so quietly remarkable. And as you imagine that deep, shadowed ocean beneath the frozen crust, a final question rises softly from the cold and the dark. What other secrets could be waiting inside a world that keeps its warmth so carefully hidden beneath layers of ancient ice? Karen entered Pluto's story in 1978 when astronomer James Christie noticed something unusual on a series of telescopic photographs. Pluto, normally seen as a simple point of light, appeared slightly stretched on certain nights, as though a small bump clung to one side. Christie checked again and again, comparing images, eliminating flaws. The bump was real. It moved. It orbited. What he had found was Pluto's largest moon, a world so big relative to Pluto that it immediately reshaped the way astronomers understood this distant pair. Charon was not a tiny satellite circling a dominant planet. It was nearly half Pluto's size, large enough that the two bodies tugged on each other with almost equal force. Because of this unusual balance, Pluto and Charon do something rare in the solar system. Instead of one body orbiting the other in the usual way, the two worlds revolve around a shared center of gravity that lies outside Pluto itself. This makes Pluto and Charon a binary system, two partners moving around a single point in space like dancers bound together by a rope of gravity. They keep the same faces turned toward each other at all times, locked in mutual tidal embrace. If you stood on Pluto, Charon would hang motionless in the sky, never rising or setting. If you stood on Charon, Pluto would do the same. Their lives are intertwined, their motions synchronized, their histories linked across billions of years. When New Horizons flew past in 2015, Charon revealed itself as a world every bit as fascinating as its partner. The spacecraft found enormous canyons slicing across its surface, some wider and deeper than the Grand Canyon, stretching thousands of kilometers in long fractured arcs. These massive rifts hinted at a dramatic past, perhaps one shaped by interior expansion. As Charon cooled over time, a subsurface ocean may have frozen and expanded, forcing the crust to crack open. The resulting canyons are stark and jagged, running along the moon's equator like scars from an ancient upheaval. Further north, Charon displays one of its most striking features, a dark red polar cap that stands out sharply against the pale greys of the surrounding terrain. This reddish material puzzled scientists at first. Charon is cold, stable, and lacks strong surface chemistry. Why would the pole be stained such a vivid colour? The current understanding is wonderfully elegant. Methane gas drifting from Pluto's atmosphere escapes into space and becomes trapped by Charon's gravity. When this methane reaches Charon's poles, regions that spend decades in darkness, it freezes out as frost. In that long polar night, ultraviolet radiation from distant space slowly transforms the frozen methane into more complex hydrocarbons called tholins. These tholins tint the polar region red, creating a cap that grows and fades with the changing seasons of Charon's long year. The connection between Pluto and Charon is deeper than simple gravitational attraction. They actively shape each other over time. Their mutual tides help maintain the stability of their orbits, preventing chaotic drifting. The locked rotation keeps both worlds facing one another, meaning each world's geography influences how heat is distributed on the other. Charon's gravitational pull may even help stir Pluto's interior slightly, encouraging the movement of materials beneath the surface. Meanwhile, Pluto supplies Charon with a slow, steady stream of atmospheric methane, building the red polar cap in a process that depends entirely on their shared partnership. Charon itself tells a separate but complementary story about the outer solar system. Its northern hemisphere appears ancient, marked by craters and rough terrain. Its southern hemisphere, however, shows signs of resurfacing, with smooth plains that hint at past volcanic or cryovolcanic activity. This contrast suggests that Charon, like Pluto, has experienced internal evolution, shifting from a warm interior in its early history to a colder, quieter world today. The smoother plains may have been formed by eruptions of ammonia-rich water in the distant past, spreading across the surface before freezing into place. If this interpretation is correct, Charon once had enough internal heat to support geological activity, far beyond what scientists originally imagined for such a small body. Together, Pluto and Charon form a system unlike anything else in the solar neighborhood. Their shared center of gravity, their synchronized motion, their mutual influence, and their eerie, beautiful landscapes make them feel like two halves of a single story. Pluto, with its bright heart-shaped basin and dynamic atmosphere, stands as the more expressive partner. Charon, rugged and scarred, offers a quieter, steadier presence. Their gravitational bond ensures that neither can fully tell its story without the other. What makes their relationship even more interesting is how balanced it is. In most planetary systems, moons are small secondary objects. They orbit at the mercy of the planet, shaped by forces far greater than their own. But Pluto and Charon are equals in many ways. They orbit together. They evolve together. They share materials, history, and motion. Each world affects the other in ways that ripple through time, creating a partnership that feels almost poetic in its symmetry. Through their long mutual dance, they have shaped each other's destinies. Pluto's tides may have helped warm Charon enough to fracture its crust. Charon's gravity may have influenced Pluto's orientation. Methane drifting from Pluto creates colour on Charon's pole, and the pair together stand as an example of how even the smallest bodies in the solar system can hold complex, intertwined lives. As you picture them circling their shared centre, two icy worlds locked in a slow, steady dance beneath the distant sun, a quiet thought begins to rise. What deeper stories unfold when two worlds spend billions of years facing each other, never turning away, never drifting apart, and never breaking the delicate connection that binds them across the cold of space. Nix, Hydra, Kerberos, and Styx drift through the Pluto-Charon system like small bright flecks caught in a quiet gravitational dance. They are tiny compared with Pluto and Charon, more like irregular blocks of ice than miniature worlds. Yet they add a layer of quiet complexity to the system, each one following a path shaped by a history that reaches back billions of years. Their presence feels delicate, almost fragile, as though even a small disturbance could shift their rhythm. But despite their size, these moons reveal an extraordinary amount about how the Pluto-Charon system formed and how it continues to evolve. When New Horizons approached Pluto, astronomers already knew these moons existed but had never seen them in detail. Their faintness made them difficult to study from Earth, and their small size meant that even the best telescopes revealed little more than points of light. But New Horizons transformed those points into landscapes, tiny, irregular bodies with bright surfaces and puzzling behavior. These moons rotate in ways that seem almost chaotic. Instead of turning steadily, like most moons, they tumble unpredictably, their axes shifting as they orbit. This strange behavior is a direct result of the gravitational influence of Pluto and Charon. which together create a gravitational field that constantly nudges and twists the smaller moons. Their rotations never settle, never lock into predictable rhythms. They spin as though they are always being slightly startled by the shifting pull of their larger neighbours. Nix and Hydra are the largest of the four, though calling them large is relative. Hydra is the biggest, stretching roughly the length of a small city. Nix is slightly smaller, shaped more like a tossed pebble than a sphere. Kerberos and Styx are even tinier, closer in size to rugged hills than full moons. Their smallness gives them unusual shapes, each one elongated or irregular, with surfaces marked by bumps, hollows and gentle curves. What surprised scientists most was how bright they appeared. Their surfaces reflect far more sunlight than expected, suggesting they are coated in clean, fresh-water ice, a material that gleams even in Pluto's weak daylight. This brightness is a clue to their origins. Clean water ice does not survive long on the surfaces of small bodies unless it is constantly renewed or protected. The most likely explanation is that these moons formed from the debris of a massive collision that also produced Charon. Long ago, a large object may have struck Pluto, blasting material into a wide disk of icy fragments. Over time, that material coalesced into Charon and the four smaller moons. In this scenario, the smaller moons inherit their brightness from the fresh ice of the collision, material that has remained relatively untouched for billions of years. Their irregular shapes support this idea, resembling fragments that never grew large enough to round themselves through gravity. Their orbits also reflect this violent beginning. The moons circle Pluto and Charon in neat, stable paths, arranged almost like gentle ripples expanding outward. Yet unlike most moon systems, where each moon rotates predictably, the gravitational tug of the binary pair keeps these smaller bodies unsettled. Pluto and Charon orbit a shared centre of gravity outside Pluto's surface, which creates a constantly shifting gravitational environment. As the pair rotate around each other, they tug at the smaller moons from different angles, preventing the moons from locking into the steady rotation that many moons settle into. Nix, Hydra, Kerberos and Styx tumble instead, turning in irregular patterns that can change from year to year or even month to month. It is unusual behaviour, but it makes sense in a system where the central objects behave more like partners than a simple planet-moon pair. The gravitational balance of Pluto and Charon is unlike anything else in the solar system, and the smaller moons respond with a kind of thoughtful unpredictability. Their tumbling reflects the deeper structure of the system, revealing just how unusual a binary world truly is. Each moon also carries hints of how the system has evolved over time. Hydra appears especially bright, suggesting its surface is dominated by clean water ice, with little contamination. Nix shows patches of light and dark, perhaps areas where darker organic materials have settled. Kerberos surprised astronomers by being darker than expected, with a surface less reflective than the others, hinting at a different role in the debris disk that formed them. Styx, the smallest, looks strangely stretched, elongated like a bead of frozen material gently pulled over time. These differences tell a story. After the Pluto-Charon impact scattered icy debris into orbit, the fragments likely collided, merged and separated again, forming a collection of distinct bodies. Larger pieces swept through the disk, gathering material until the system settled into its present arrangement. The diversity of the moons shows that this process was messy, governed by countless small collisions, gravitational nudges and slow accretion. Each moon is like a frozen memory from that ancient era, shaped by chance and preserved in the cold. Because they are so light and so far from the sun, These moons drift almost unchanged through time. Their surfaces are quiet, untouched by atmosphere or flowing ice. Craters mark their histories, but even cratering is limited in the distant Kuiper belt. Their brightness means very little dust has settled. Their small size means geological activity is unlikely, so they remain simple, silent bodies, reflecting the light of a distant sun as they tumble through the darkness. Yet even in their simplicity they reveal something profound. They show that the Pluto-Charon system is not a lonely world with a single satellite. It is a small, stable community, shaped by a single ancient collision and held together by delicate gravitational ties. Nix, Hydra, Kerberos and Styx give the system a sense of depth, extending its story beyond Pluto and Charon and into a network of tiny companions that each play their part. Their presence also gives perspective on how rare and intricate small systems can be. In a solar system filled with vast planets and powerful forces, the Pluto system stands as a reminder that beauty can exist even in the smallest of arrangements. 4 tumbling moons, born from ice and impact, following paths shaped by a binary pair, drifting through darkness with surfaces that shine brighter than expected. As you picture them spinning in their quiet orbits, bright specks reflecting the faint light of a distant sun, a soft question begins to form. How many other small hidden worlds across the outer solar system carry stories just as subtle, just as delicate, waiting for someone to notice the way they shine? New Horizons began its journey with quiet determination, slipping away from Earth in January 2006 on a trajectory that would send it across the solar system faster than any spacecraft launched before it. The mission carried a simple purpose: to reach Pluto, a world that had lived for decades as a distant speck of light. It would be a one-time encounter, a single moment of closeness, the briefest of visits after nearly a decade of flight. Yet that single moment would reveal an entire world that no one had truly seen before. As New Horizons left Earth behind, it carried not only its instruments and antennas, but a sense of anticipation that stretched across continents, generations, and years of scientific dreaming. The early part of its journey was swift. It flew past the Moon in less than 10 hours. It raced onward toward Jupiter, where it performed a gravity assist that flung it even faster toward the outer solar system. And then came the long, quiet years. New Horizons drifted through space at tremendous speed, but even that speed felt slow when measured against the staggering distances involved. It travelled millions of kilometres, then hundreds of millions, then billions, leaving the inner planets far behind. Its instruments were powered down for much of this time, waking only occasionally for check-ins, calibrations, and course adjustments. The spacecraft spent these years in a kind of technological hibernation, conserving energy for the brief window when it would finally meet Pluto. The quiet of this cruise phase often goes unnoticed, but it forms a moving part of the mission's story. For nearly a decade, New Horizons travelled through a region of space so empty that even sunlight felt stretched thin. It experienced nothing of weather, nothing of sound, nothing of immediate urgency. It simply continued, hour after hour, day after day, year after year, crossing the enormous void with unwavering purpose. If a person had somehow been aboard, they would have seen the sun shrink slowly, turning from a bright disk into a bright star. They would have watched the surrounding darkness grow deeper, and they would have felt the vastness of space in a way few humans ever have, not as an idea, but as an environment made of silence. As New Horizons approached Pluto in 2015, the pace suddenly changed. The spacecraft awoke fully and began its preparations. Instruments warmed and calibrated. Cameras turned toward a tiny point of light growing incrementally larger. Engineers on Earth watched as that point began to resolve into a small, blurry circle. For Pluto, this was the first time in its entire existence that it would be seen up close by a visitor from another world. For New Horizons, it was the moment its years of drifting finally became meaningful. The closest approach occurred in July 2015. For a single day, the spacecraft rushed past Pluto at tens of thousands of kilometers per hour, gathering more data than it could transmit quickly. Images, spectra, measurements, and observations filled its memory. Every camera snapped photo after photo. Every instrument recorded details as Pluto's surface, atmosphere, and environment. It was a moment of intense activity compressed into a timescale measured in minutes. Then, as quickly as the encounter began, it was over. New Horizons continued into the Kuiper Belt, leaving Pluto behind as a completed chapter in its long journey. When the first detailed images reached Earth, the reaction around the world was immediate. Pluto was no longer a distant dot. It was a place, a world with a heart-shaped plain, towering mountains of water ice, smooth expanses of nitrogen glaciers, and a sky glowing blue with delicate haze. No one had expected such complexity. No one had imagined that a tiny world at the edge of the solar system could look so alive. Scientists and the public alike were astonished. The images felt almost emotional, as though a long-lost relative had finally stepped into the light. The scientific surprises came quickly. Pluto's surface was far younger and more active than expected. Entire regions lacked craters, suggesting recent geological activity. The nitrogen ice in Sputnik Planitia formed polygons that hinted at convection. The mountain ranges, made of solid water ice, defied predictions that Pluto should have cooled into complete inactivity. The atmosphere revealed layers of haze rising more than 200 kilometers above the surface. Every image contradicted old assumptions. Every measurement deepened the mystery. Charon too surprised scientists. Its vast canyon system stretching across its equator suggested internal processes that once reshaped the moon from within. Its dark red polar cap revealed a chemical partnership with Pluto's escaping methane. Its plains showed evidence of resurfacing, hinting at ancient cryovolcanism. The moon's Hydra, Nix, Kerberos, and Styx tumbled unpredictably, their bright surfaces reflecting the fresh ice of their ancient origins. The entire system, once assumed to be simple, was instead a tapestry of complexity. One of the most powerful moments came when New Horizons turned back toward Pluto and photographed the world in silhouette. Against the blackness of space, Pluto was rimmed with a glowing blue halo, its atmosphere scattering sunlight in a soft, ethereal ring. That single image changed the emotional tone of the mission. It showed Pluto not as an icy leftover, but as a world with colour, light, and presence. A world capable of subtle beauty even at the farthest reaches of the solar system. The data New Horizons returned continued to surprise scientists long after the flyby ended. It redefined ideas about geological activity in cold environments. It demonstrated that worlds as small as Pluto can hold heat for billions of years. It reshaped theories about the Kuiper Belt, revealing that icy bodies can evolve in complex ways. It expanded the list of potential ocean worlds, raising questions about how many other small planets may hold liquid water beneath their crusts. For the broader public, the mission transformed Pluto from a distant concept into something relatable and vivid. People saw a world with a heart-shaped plane, and they felt something human in that image. They saw mountains, valleys, and a sky glowing blue. They saw a world that had been waiting for a visitor since the solar system began. New Horizons showed that exploration is more than the collection of facts. It is the quiet crossing of great distances, the patience of long travel, the beauty of first contact, and the surprise of discovering that the unknown is often far more intricate than imagined. It is the reminder that even worlds on the edge of everything can hold wonders, waiting quietly for the moment someone finally reaches them. And as New Horizons continued into the Kuiper Belt carrying its memories of that brief encounter, one thought lingered softly in its wake. How many other worlds are waiting in the darkness, holding stories no one has yet seen? Pluto changed the way scientists think about small, icy worlds. Before New Horizons arrived, the general expectation was that a world as tiny and distant as Pluto would be cold, quiet, and geologically silent. Its surface would be old and cratered. Its atmosphere would be thin and temporary. Its interior would be frozen solid. Everything about it, according to older models, should have resembled a relic from the early solar system, ancient, unchanged, and simple. But the moment the first high-resolution images arrived, those assumptions dissolved. Pluto was not simple at all. It was active, textured, layered, and full of surprises. It taught scientists that small worlds can behave like planets much larger than themselves, and that geological activity is not the sole privilege of heat, mass, or proximity to the sun. One of the most important lessons Pluto offered is that cold does not mean dead. Its surface revealed smooth plains with almost no craters, indicating recent resurfacing. Mountains of water ice rose like jagged spires. Glaciers of nitrogen ice crept across the landscape in slow, steady flows. Deep faults stretched across the surface, suggesting tectonic forces at work. None of this aligned with the old view that worlds shrink into silence as they lose internal heat. Instead, Pluto proved that even a small, icy world can store enough warmth to drive movement for billions of years. This warmth may come from radioactive decay in its interior, or from the insulating effect of thick layers of ice, or from chemical mixtures that lower the freezing point of internal water. Whatever the source, Pluto showed that cold planets can still be alive with quiet motion. Pluto also expanded the idea of cryovolcanism. Cryovolcanoes are volcanoes that erupt not molten rock, but cold materials like water, ammonia, or methane. Before New Horizons, cryovolcanism was mostly associated with moons like Enceladus or Triton, worlds shaped by tidal forces from giant planets. Pluto, lacking a giant neighbour, was not expected to show similar behaviour, yet surface features hinted that it may have experienced cryovolcanic eruptions in the distant past. Some regions, especially around the mountain Right Mons, suggest uplift and smooth surfaces that might have been formed by the outflow of slushy water-ammonia mixtures. These features are not confirmed volcanic structures, but they look different from impact craters or tectonic fractures. They support the idea that Pluto once pushed internal materials upward through its crust, reshaping the surface with ice rather than molten rock. This possibility reshaped ideas about how planets evolve. Scientists once believed that cryovolcanism required strong tidal heating, but Pluto showed that internal heat alone may be enough. If Pluto can produce such features without being stretched and squeezed by a giant planet, then many other distant worlds might be capable of similar activity. This suggests that geological evolution is far more varied and resilient than previously imagined. Pluto also taught scientists that icy surfaces can behave in ways that mimic familiar geological processes. Nitrogen ice, for example, flows like glaciers on Earth, forming troughs and ridges and carrying darker particles with it. Methane ice brightens elevated regions. Carbon monoxide plays a role in reflectivity. These exotic ices form landscapes that resemble those shaped by water, wind, and volcanic activity on Earth, but through entirely different mechanisms. The world became a natural laboratory for geology at temperatures far below what terrestrial scientists typically study. The tectonic features on Pluto provided another lesson. The deep fractures stretching across its surface are unusually wide and clean. They suggest that Pluto's crust expanded over time, possibly as an internal ocean slowly froze and expanded, pushing the crust outward. This behavior supports the idea of subsurface oceans on small worlds and hints that such oceans may be common in the outer solar system. The cracks also indicate that Pluto's shell is thick and strong, capable of transmitting stresses across large distances. This strength is a direct result of extreme cold, which transforms water ice into a material harder than granite. In this way, Pluto flipped expectations again, showing that geological features usually associated with strong internal processes may instead be sculpted by the materials themselves. Another insight Pluto offered relates to the early solar system. The Kuiper Belt, once considered a quiet region full of simple icy bodies, turned out to be home to worlds with rich geological histories. Pluto's composition, atmosphere and surface activity suggest that the objects in the outer solar system are more complex than early theories predicted. Instead of representing untouched leftovers, they may have experienced heating, melting, differentiation, and resurfacing. Pluto's nitrogen ice plains, methane frost, organic compounds, and possible ocean all hint at a world altered by processes that unfolded over billions of years. This encourages scientists to look more closely at other Kuiper Belt objects and consider what secrets they might hide. Pluto also reframed what it means to be a small world. Before the New Horizons flyby, there was a simple division between planets and minor planets, between large worlds with active geology and small icy bodies regarded as static. Pluto blurred that line. It demonstrated that small worlds can be layered, dynamic, and full of ongoing processes. It showed that the presence of an atmosphere does not depend on size alone. It revealed that icy objects, even those barely large enough to hold spherical shapes, can store internal heat for vast stretches of time. Pluto's very existence challenged long-held assumptions about what worlds are capable of. One of the most unexpected lessons came from its atmosphere. Pluto's thin blue haze revealed that even in places where sunlight is little more than a faint glow, complex atmospheric chemistry can flourish. Methane breaks apart in the upper layers, forming hydrocarbons that drift down toward the surface. These particles create the reddish hues seen across Pluto's face. The layered haze rises hundreds of kilometers above the ground, shaped by waves and temperature gradients. The atmosphere freezes out in winter and reappears in spring, showing that worlds can have seasonal cycles even with extremely thin air. Pluto's atmosphere proved that complexity does not require density. It only needs the right ingredients and time. Another lesson lies in the role of the Pluto-Charon system. Their unusual double orbit and gravitational balance influence each other's surfaces, rotations, and geologic histories. Material escapes from Pluto and collects on Charon's poles, creating the red cap. Tides between the two bodies may have driven early internal evolution. Their shared center of gravity affects the behavior of the smaller moons. Together they form a miniature system more intricate than anyone expected, showing that even tiny planetary pairings can hold deep scientific value. Pluto taught scientists that the solar system is not neatly divided into categories of active and inactive worlds. It is not a place where only large planets matter. Instead, it is filled with surprises, small worlds with internal oceans, distant bodies with atmospheres, and icy regions with unexpected heat. It taught researchers to be cautious with assumptions, to leave room for wonder, and to expect that even the most distant objects may hold stories that challenge our understanding. But perhaps the most important lesson Pluto offered is emotional rather than scientific. It reminded the world that exploration is worth the time, the patience, and the long years spent drifting through darkness. It showed that beauty and complexity are not limited to the bright inner solar system, but extend all the way to the edge, where sunlight is weak and time moves slowly. It taught us that no world is too small or too distant to surprise us. And as all these lessons settled into the scientific community, one question rose softly through the new understanding. If Pluto, a world once dismissed as a cold, simple remnant, can hold so much depth, what else in the outer darkness might be waiting to reshape our view of the universe all over again? In 2006, a quiet meeting in Prague changed the way the world thought about Pluto. Astronomers from around the globe gathered to answer a question that had lingered for years. What exactly is a planet? It was not a question of sentiment or tradition. It was a question of definition. The solar system was growing, not through new planets, but through the discovery of many large objects in the Kuiper Belt. One of them, Eris, appeared to be roughly the same size as Pluto. If Pluto was a planet, then should Eris be one too? And what about the dozens of similar icy worlds that were likely waiting to be discovered? The need for clarity had finally reached a point where the scientific community felt a formal definition was necessary. Before this meeting, planet had no official scientific definition. It was a word passed down through history, shaped more by culture than by consistent criteria. Mercury, Venus, Earth, and Mars were planets, because ancient astronomers saw them wandering across the sky. Jupiter and Saturn were planets for the same reason. Later, Uranus and Neptune joined the list because telescopes revealed their presence. Pluto was added in 1930 simply because it appeared to be the next object in the sequence of discoveries. No formal rules guided these choices. It was tradition layered on tradition. But science evolves, and by the early 2000s, discoveries in the outer solar system forced astronomers to reconsider. The Kuiper Belt was filled with icy bodies, some small, some unexpectedly large. Pluto suddenly looked less like a unique outpost and more like a member of a large family. Without a clear definition, the list of planets could swell to 20, 30, or more. The solar system would look very different on paper, and scientists needed a framework that reflected structure rather than chance. The final definition adopted by the International Astronomical Union was simple on paper, but powerful in effect. To be a planet, a world needed to meet 3 criteria. First, it had to orbit the Sun. Pluto fit that. Second, it had to be massive enough for gravity to pull it into a nearly round shape. Pluto fit that too. The third requirement was the crucial one. It had to clear its orbital neighborhood of other objects. In other words, it needed to be gravitationally dominant, sweeping smaller bodies aside as it travelled. Pluto, drifting within a dense region of Kuiper Belt material, did not meet this requirement. It shared its orbital zone with many other icy objects. By the new definition, it was reclassified as a dwarf planet. Scientifically, the reasoning made sense. The new definition reflected the architecture of the solar system, distinguishing between worlds that shape their orbits and worlds that coexist with other debris. But the change struck an emotional chord with the public. Pluto had been taught in classrooms for generations as the ninth planet. Millions of people had grown up imagining a small, distant world circling the sun at the edge of everything. The demotion felt personal, even though the world of Pluto itself remained unchanged. It still orbited. It still shone faintly in the dark. It still held its mountains, plains, and mysterious atmosphere. What changed was only the label. Arguments in favor of restoring Pluto's planetary status came quickly, and they continue to this day. Some astronomers argue that the third criterion is unfair, because gravitational dominance depends heavily on distance from the Sun. If Earth were moved to Pluto's orbit, it would also fail to clear its neighborhood. Others suggest that geophysics should be the defining factor. If a world is round, differentiated and shaped by internal processes, then it behaves like a planet and should be called one. By this standard, Pluto qualifies with ease. It has active geology, layered ices, possible cryovolcanoes, and perhaps a subsurface ocean. It is far from a simple object. Another argument leans on the spirit of exploration. When New Horizons revealed Pluto's vast nitrogen plains, towering mountains, and blue atmospheric haze, many people felt the world deserved the term planet, simply because of its complexity. The images stirred something human, a sense that Pluto was more than an icy fragment. It was a place with personality, science, and story. A place that had waited quietly for billions of years until a spacecraft passed close enough to reveal its face. Those who support the current classification make valid points as well. They argue that categories should reflect physical structure and dynamical behavior, and that dwarf planets are no less fascinating than the larger ones. The term dwarf does not diminish Pluto. It simply places it in a group with others of similar history and composition. In this view, dwarf planets represent a branch of planetary evolution worth studying for its own characteristics rather than its resemblance to Earth or Mars. Perhaps the most enduring aspect of the planet debate is the emotional connection people feel toward Pluto. Few scientific classifications spark such widespread response. The outcry after 2006 came not only from astronomers but from children, teachers, writers, and families. People felt protective of Pluto, as though its identity reflected something nostalgic and comforting. Pluto had been the small, lonely world at the edge of the map. It represented curiosity, possibility, and the sense that even distant places deserved attention. When its status changed, it felt like a story had been rewritten. But in reality, Pluto did not lose anything. It did not shrink. It did not dim. Its mountains remained tall, its glaciers continued their slow migration, and its atmosphere still glowed blue at sunset. The world itself stayed exactly as it had been. What changed was only the language humans used to describe it. And as time has passed, many have come to see that Pluto's richness and beauty grow more compelling the more we learn about it. Whether called a planet or a dwarf planet, it remains one of the most surprising worlds in the solar system. The debate may continue for decades. Definitions evolve. New discoveries challenge old ideas. As more worlds are found in the Kuiper Belt and beyond, perspectives will shift again. But through it all, Pluto holds a unique place in both science and imagination. It represents the way exploration reshapes understanding and the way understanding reshapes emotion. It stands as a reminder that the universe is full of worlds that defy simple labels. In the end, Pluto's story shows how science evolves as new evidence appears, reminding us that understanding the solar system is less about labels and more about learning how each world works in its own quiet way. Pluto has always lived partly in the human imagination. Long before New Horizons revealed its mountains and glaciers, it existed as an idea, a small, distant world circling the sun in near silence. For many people, that quiet distance made Pluto feel strangely relatable. It was the last planet on school posters, the little one on the edge, the outsider that still belonged. It appeared in storybooks, classroom models, documentaries, and the kind of childhood conversations that happen while looking up at the night sky. Even without detail, Pluto held a presence. It was the world you heard about when learning the planets for the first time, the final name in that familiar list. Something about that position made it feel like the shy character in a story, far away, but still part of the family. As science slowly uncovered more truth about Pluto, imagination continued to fill the gaps. Early drawings showed it as a smooth, frozen sphere wandering alone. Some stories gave it seas of methane or cities beneath the ice. Films and novels used it as a backdrop for mystery, isolation, or discovery. It was the blank page at the edge of the solar system, a place where writers and artists could project anything they wanted. Even in scientific diagrams, Pluto's position made it symbolic. It was the border between the known and the unknown, the place where the map faded. The idea of a distant, lonely world naturally stirs empathy. Humans tend to look at remote places and give them character, especially when those places appear small or overlooked. Pluto seemed to fit that role perfectly. It was discovered late, faint in the sky, orbiting far beyond the bright planets. It appeared fragile compared with Jupiter or Saturn. It had a long, slow year and a tilted axis that made its seasons unusual. All these details contributed to the feeling that Pluto was a quiet world trying its best in a harsh environment. People projected emotions onto it, not because Pluto asked for them, but because the image of a tiny world enduring deep cold resonates with how people sometimes feel themselves. Even mythology plays a part in Pluto's identity. The name, inspired by the Roman god of the underworld, added an air of darkness and mystery. It felt fitting for a world receiving only faint light, orbiting in a region few had imagined in detail. But mythology blended with science in unexpected ways. Instead of a gloomy underworld, modern observations revealed a world with bright ice, pale mountains, and soft atmospheric haze. Pluto became both mythic and scientific, shaped by ancient stories yet redefined by data. This mix helped keep Pluto in the public imagination long after it was reclassified, long after debates over its status faded in the news cycle. The reclassification in 2006 did something unusual. It made people speak about Pluto with protectiveness. Children wrote letters asking for its status to be restored. Teachers continued using old posters because they felt attached to the 9-planet layout. Artists created illustrations showing Pluto looking confused or left out. It was one of the rare times when a scientific update produced a cultural ripple. People were not just responding to a change in terminology, they were responding to a story they had grown up with. Pluto had been part of that story, and the idea of moving it into a different category felt like losing a character halfway through a book. When New Horizons sent back its images, the cultural impact deepened. Suddenly Pluto was not just a symbol, it had a face. The heart-shaped plane became an instant icon. Newspapers featured it. Social media flooded with it. People described it as sweet, welcoming, or poetic. Scientists smiled at the attention, knowing the heart was simply a large nitrogen basin shaped by geology, but appreciating that people connected emotionally with the image. Fiction and art absorbed this new detail quickly. Illustrators gave Pluto a warm personality. Animators placed characters on the bright plains. Writers described the heart as a sign of resilience. A scientific feature became a cultural emblem almost overnight. Why does Pluto inspire this response more strongly than many larger or more dramatic worlds? Part of the reason lies in its contrast. When something small reveals unexpected depth, people tend to notice. Pluto was expected to be simple. Instead, it turned out to be layered, textured, and full of movement. That surprise created affection. It was like opening a small, unassuming box and finding something intricate inside. The emotional reaction followed naturally from the shift in expectation. Another reason is distance. Pluto lives far beyond the orbit of Neptune, in a region where sunlight weakens and temperatures plunge. Its remoteness gives it an atmosphere of calm and endurance. When people imagine a world that quietly persists through long winters and faint light, they project qualities like patience, resilience, and solitude. Even though Pluto is indifferent to such ideas, the human mind gravitates toward them. Stories keep Pluto present in everyday thought. It appears in animations, novels, games, and poetry. Some portray it scientifically, others use it as a symbol for isolation, curiosity, or transformation. In classrooms, Pluto often becomes a discussion point about how science changes. Teachers use it to explain that knowledge evolves, that definitions shift, and that learning is an ongoing process rather than a fixed list of facts. Pluto becomes a way to show students that exploring the universe sometimes leads to revisions, and that revision is a sign of progress rather than error. Scientific discoveries reinforce these stories rather than replace them. Images of Pluto's glaciers, haze layers, and mountain ranges add detail that artists and writers can build upon. Instead of contradicting imagination, the real Pluto gives storytellers more to work with. The surface's variety, the possible presence of a subsurface ocean, the connection with Charon, and the presence of smaller moons expand the narrative. Pluto becomes a world with depth, rather than a blank canvas. There's also something appealing about the way Pluto balances harsh conditions with gentle features. The cold is extreme, yet the landscape includes smooth plains. The atmosphere is thin, yet it glows a soft blue. The heart-shaped basin looks inviting despite being made of frozen nitrogen. This mixture of extremes creates a poetic tension that captures people's attention. It feels like a world that should be desolate but instead reveals quiet beauty. In a broader sense, Pluto reflects the emotional side of science. Exploration is not only about numbers and measurements, it is also about curiosity, hope, and the feeling that the universe contains places worth reaching even if they seem distant or small. Pluto sits at the edge of the familiar solar system. Reaching it required ambition, patience, and nearly 10 years of travel. When the images returned, they carried not only scientific information, but a sense of accomplishment. People saw the photographs and felt connected, not just to Pluto, but to the idea of human exploration itself. Pluto's cultural role continues to evolve. New scientific papers bring more details. Artists reinterpret old ideas. Children still draw it with big eyes and a smile. Authors still place characters on its icy plains. and educators still use it to talk about how science works. Through all these forms, Pluto remains more than a world. It becomes a shared idea, a soft point of imagination that offers both inspiration and comfort. And as Pluto settles into this dual identity, both scientific and symbolic, it leaves behind a quiet impression. Some worlds resonate not because of their size or status, but because something about them simply stays with people once they are seen. A future mission to Pluto would begin with the same sense of anticipation that surrounded New Horizons, but this time the plan would be very different. Instead of a fast flyby that offered only a single day of close observation, scientists now imagine a spacecraft that slows down as it approaches and settles into a long orbit. The idea of circling Pluto for months or even years fills researchers with a quiet excitement. An orbiter would allow them to watch the world change with time, to see how frost drifts and settles, to monitor the faint atmosphere as it thickens and thins, and to follow the slow patterns of the nitrogen glaciers across the plains. It would be a chance to see Pluto not as a snapshot, but as a place that lives and moves through its long seasons. Designing such a mission would take patience. The spacecraft would need to travel for many years and then make a careful series of maneuvers to slow itself enough to be captured by Pluto's weak gravity. The journey would be long, but the destination justifies the effort. After all, the last time a visitor arrived, it changed almost everything scientists believed about distant icy worlds. An orbiter would offer the kind of lingering presence needed to understand Pluto at a deeper level. It could map the entire surface in fine detail, track changes across the long Plutonian day, and reveal which regions evolve over time and which remain frozen in place. One of the biggest scientific goals would be to investigate Pluto's interior. The possibility of a hidden ocean beneath the icy crust is one of the most intriguing questions left by New Horizons. An orbiter could fly repeated paths over the same regions, measuring tiny shifts in Pluto's gravity. These measurements would allow scientists to create a picture of what lies inside, layer by layer. If the crust is floating on liquid water or a softer, partially melted layer, the spacecraft would detect the subtle sway of the surface as it responds to internal movement. Discovering a liquid reservoir beneath Pluto's shell would reshape ideas about how small worlds retain heat and how they evolve over billions of years. Some mission concepts also include radar instruments able to look beneath the surface. Radar could reveal buried structures, layers of or possible pockets of softer material. It could show whether the crust is uniform or varied. It might even detect fractures or ridges hidden beneath the frost. With these tools, scientists could build a three-dimensional understanding of the world, rather than relying on surface appearance alone. Another important priority is direct analysis of Pluto's surface. A lander would be challenging but enormously rewarding. The low gravity and extreme cold require careful engineering, yet the scientific payoff would be significant. A lander could scoop small amounts of nitrogen ice, methane frost, or darker organic particles and analyze them on the spot. Even a few samples would carry information about chemical processes, atmospheric cycles, and the long history of surface changes. The composition of these ices would help scientists understand how Pluto formed and how the outer solar system has evolved over time. A more flexible option is a small hopping vehicle. In Pluto's low gravity, a modest push from a cold gas thruster could lift a hopper from one region to another, allowing it to explore multiple sites during a single mission. It could touch down on the smooth plains, leap toward the foothills of a water ice mountain, and travel to darker, more ancient terrain farther away. A hopper could study regional differences in composition and texture, revealing how Pluto's surface varies across its complex landscape. Any return mission would also revisit Charon. New Horizons showed that Pluto's largest moon is a world with its own story, complete with massive canyons and smooth plains hinting at a dynamic past. An orbiter could map Charon's surface with high precision, revealing structures too small for the flyby to capture. It could study the dark red polar cap and confirm how methane from Pluto transforms into complex organic material during the long polar night. It could analyze the fractures that stretch across the surface and investigate whether Charon once had a warmer interior capable of reshaping its crust. The 4 smaller moons also deserve attention. Nix, Hydra, Kerberos and Styx rotate unpredictably, and scientists want to understand how the gravitational pull of the Pluto and Charon pair influences them. An orbiter could watch these moons over time, tracking their movement and behavior in a way no Earth-based telescope ever could. It could map their reflective surfaces and search for signs of variation in their composition. Studying these small moons offers clues about the ancient collision that likely formed the entire system. Their shapes, rotations, and surface features still carry signatures of that event, preserved in the cold. Some mission proposals include atmospheric probes designed to drift gently through Pluto's thin sky. These small craft could sample the haze particles directly, collect tiny grains of hydrocarbon dust, and measure how temperature and pressure change with altitude. They could watch the atmosphere collapse as winter approaches, or study how it expands during the long spring. Understanding these cycles would deepen knowledge of how atmospheres evolve in extreme environments. Another idea is a dedicated sample return mission. This would be ambitious and would take decades, but the notion of bringing a piece of Pluto back to Earth is tempting. A few grains of nitrogen frost or a small patch of methane ice would provide a treasure of chemical information. Scientists could study the samples in laboratories far more precise than any instrument that could fit on a spacecraft. Even a tiny amount of material could reveal details about the building blocks of the early solar system, the chemistry of distant ices, and the processes that shape worlds in the deep cold. There is also the potential for exploring beyond Pluto once an orbiter completes its studies. The Kuiper belt contains countless icy bodies, many of which remain unexplored. A spacecraft already in the outer solar system would be well placed to visit additional targets. It could fly past another Kuiper belt object and compare its surface with Pluto's, expanding understanding of how diverse these distant worlds truly are. Such a mission would not only deepen Pluto's science, but widen the picture of the entire outer region. The power of a future mission lies not only in the discoveries it might make, but in the time it would spend observing. Many of Pluto's most interesting processes unfold slowly. The gases in its atmosphere change over decades. Frost patterns shift across seasons that last longer than human lifetimes. Glaciers creep in tiny increments. To understand these changes, scientists need long-term observation. An orbiter could watch these slow transformations, capturing details that a single flyby could never reveal. A return mission would also answer lingering questions about why Pluto is so active. It could determine whether the internal heat source is steady or fading. It could measure how quickly the atmosphere collapses and reforms. It could determine how long the nitrogen plains retain their smooth texture before becoming marked by new impacts. It could reveal whether the mountains continue to shift ever so slightly, or if the crust has locked into place. There is a sense of quiet optimism among scientists when they talk about returning to Pluto. They know that the journey would take years and that the challenges are significant. Yet they also remember the moment New Horizons showed the world Pluto's bright plains and blue sky. That moment proved that the outer solar system still holds surprises worth travelling toward. A future mission would build on that legacy, offering not just new facts, but a deeper sense of how this distant world fits into the story of the solar system. Whatever form the mission takes, one thing is almost certain. When humanity returns to Pluto, the world will reveal details that no one expects. It has done so every time it has been studied, and there's no reason to believe the pattern will end. The next visit would not just refine current knowledge, it would shift understanding again, opening new questions and offering new perspectives on the frozen worlds that drift in the quiet beyond Neptune. Pluto settles gently in the mind after a long journey. It begins as a distant point of light and slowly becomes a place with texture, colour, and story. Its mountains rise from water, ice-hardened by the cold. Its plains hold frozen nitrogen that shifts in slow, patient flows. Its thin atmosphere glows with soft blue light when touched by the far-off sun. Every part of Pluto carries a sense of quiet resilience, shaped by conditions that would silence most worlds, yet somehow allowing beauty to emerge in the darkness. Across this journey, each layer of Pluto revealed something different. The surface showed a landscape far more active than anyone expected, filled with glaciers, smooth basins and ridges where the crust has stretched. The atmosphere added a calm, drifting presence above the plains, forming haze layers that reach far upward. The moons created a small family around Pluto, each with its own history and character, from the vast canyons of Charon to the bright surfaces of the smaller companions. Together they formed a system that feels complete in its own quiet way. The story of exploration added another dimension. New Horizons transformed Pluto from an idea into a world, showing what patience and curiosity can achieve. For nearly a decade, the spacecraft travelled in silence, heading toward a place no one had seen up close. When the images finally arrived, they carried both scientific detail and a sense of wonder. They reminded everyone that distant worlds do not need to be large or warm to be captivating. Sometimes they simply need to be themselves. Pluto's place in culture added a softer note. It has long lived in memories as the small world on the edge, the final name in a familiar list. Its reclassification did not lessen its meaning. If anything, it strengthened the connection people feel. Pluto became a symbol of curiosity, of change, and of the way science grows. It showed that learning about the universe is not just about facts, but about how those facts make people feel. As this journey settles into a gentle close, the image of Pluto remains calm and steady. A distant world circling the sun in long, slow arcs. A world that holds its own rhythm, its own quiet weather, its own hidden depths. A world that continues to surprise scientists and comfort dreamers. Its light may be faint, but its presence is steady, waiting patiently in the outer darkness. And now, after travelling through its history, its landscapes, its sky, and its meaning, the mind can rest with a sense of calm. Pluto remains out there, unchanged and unhurried, a small companion at the far edge of the solar system, a reminder that even the quietest worlds have stories worth listening to, especially at the end of the day.